So today is Kosiketi, okay. Kokukelani. For this is Amuzuvi, Keti, Tibekabe, and Kolani. So we have Kolani, we have Keti, we have Dr. Tibekabe, Mr. Tibekabe, and we are missing Amuzuvi. Do you any news from Kosi?
Yes. So he was asking if it's possible to put him in the fourth position.
Fourth position.
Yeah,
that is something we should deal with the other person. So, Mr. Katie, please, is it possible that you start? Because Mr. Muzubi has a little problem. So we should a little shift the order of presentations. So if it's possible that Mr. Katie starts and after Mr. Tibekabe and Mr. Kolani, and then we will end with Dr. Muzobi. Is it possible for you, please?
Oh.
Hello.
Yeah.
Do we have your authorization? Mr. Katie, are you with us?
I think he said yes.
Ah, okay. Yeah. And Mr. Chebekabe, unmute. Yeah.
Hello.
Hello, yeah.
Hello, Miss Dr.
Do we have your authorization?
We can start.
Okay.
Yeah, we can start. I'm ready.
Okay, and we finish with Mr. Kolani. It's okay also for you? Hello. Mr. Kolani. Mr. Kolani. He's not there. Okay. Anyway, Mr. Kolani, you'll make your presentation 20 minutes before the time of the schedule. Is it possible? Okay. He's not there. Doctor.
Hello, do you say Mr. Folabi or Mr. Ibrahim? I can't hear that clearly.
No, Kolani. I said Mr. Kolani.
Okay.
Mr. Kolani. Koku Kolani, are you there? Okay. Dr. Mocho.
Yep. We have.
So, who will be the chairman of this morning? Yes.
Prof. Soguti. So he was around. Now he disappears.
He left. Maybe yesterday he had some problem with his connection. So he said that he tried for almost 1 hour before succeed. So okay. I hope this. I hope this morning he will not have the same problem.
No, if Prof Sugut is not around, I would take over.
Okay.
So you can do the host.
Okay. So I'll let you.
I hope there's no challenges this morning.
So Dr. Dambe, you are now the host. You can manage.
Okay. Okay. Thank you.
Dr. Laremu? I thought everybody was unmuted.
So I think we should try to start. It's now.
Still have 4 minutes.
Yeah, but we just prepare the presentation and share screen before. So it's Mr. Katie who will start. So Mr. Kitty, can you share your screen? Mr. Kitty, you can start sharing your screen and prepare yourself. You have 4 minutes before. Mr. Kitty,
Mr. Kosi KTI, can you hear us? Okay. And I'll then ask Mr. Kabe to be ready to take over Mr. Katie, so that we don't delay too much. Okay, I think early is not to be early is not bad. So if everyone is ready, let's welcome Mr. Kosiketi for his presentation. So Mr. Kosiketi is coming from, is it ICTP, and he's going to present his work on density functional theory on a lattice. So Mr. Kosi, the floor is yours. You have 15 minutes for presentation and then 5 minutes for questions and answers.
Okay, thank you. Good morning, everyone. My name is Kosi Kechi, or actually MC student at ICP Alpha. So I will present this work who was done at the African Institute for Mathematical Science, Cameroon Center. Okay, this is the outline I will follow. I will present background on DFT. After I will present the Huber model and a brief study of the Huber dilemma. And I will present the DFT formalism for the Huber model, and we study the fundamental gap and we conclude. So this presentation was planned for 30 minutes, so there are some parts that I will skip and maybe we can come back on it on question. So the many body problem in quantum physics is a well-known and complicated problem. So if you want to describe electronic system, we need to write down the Hamiltonian, taking into account all the interactions. So the first term is the nuclear kinetic energy, the second term is the electronic kinetic energy, and this potential, the nuclear interaction, nuclear electron and electron interactions. This problem is a very complicated problem and there is no way to make a progress. The program is complicated, and the Paul Dirac in this famous paper named Quantum Mechanics of Many Electron Systems said that chemistry has come to an end. And he said that the large part and the law necessary for the mathematical treatment of large part of physics and the whole of chemistry are completely known. But the difficulty is how to solve exactly these equations. And Dirac was talking about the Schrödinger equation describing the many body problem. So the first attempt to this problem is the so-called the Born-Oppenheimer approximations. So where we assume that the motion of the electron is fast due to its mass than the motion of the nuclei. So we can separate the wave function into wave function where the electronic wave function depend parametrically on the nuclear positions. So doing this and with some mathematics, we can come up with two equations. That is the electronic Schrödinger equation and the nuclear Schrödinger equation. So from now, we focus on the electronic Schrödinger equations. And there are some method known as the wave function method to solve these equations. So like the variational principle, so we minimize the Hamiltonian, and the ground state energy is just the minimum of the energy defined by this equation. So yeah, before there is the Archifock method, which assume that the wave function is a single Slater determinant, and these phi I are the spin orbitals. So, and he minimized this uh, expectation value of the Hamiltonian with respect to the constraint of normalization of the spin orbitals. So, and he came up with these n integral differential equations that can be solved using a self-consistent calculation. So I will come back talking about self-consistent calculation when I will present the GFT. So, but this wave function method has hit what the Watercone calls in his Nobel lecture the exponential wall. So the wave function is 3n dimensional. For instance, if you want to describe or to store the wave function of iron, where the atomic number is 26, we need like 78 variable. And if we discretize the space, maybe using 10 entries, this will need 10 to power 17. So this is like, there is no actually computer that can store this kind of uh, values. So that's what I can call the exponential wall. So we need to find another method to describe or to approximate this. But before that, I want to like make a precision. So if we take two systems, the difference between the Hamiltonian is essential the number of electron, the charge, and the nuclear positions. So we can, if we know the density, if someone give you the density defined as equation 13, you can actually compute the number of electron by just integrate the density. And we all know that the density has a curve. For instance, this I drew for the atomic molecule, like for instance, the dihydrogen, the density has a curve as nuclear positions. So if you can find the positions of the nuclei, and also there is this condition that called the Kato-Skurps condition that you can use to find the nuclear charge. So this means that if someone gives you the electronic density, you can actually construct fully this Hamiltonian. So this proves that one can replace the wave function by the electronic density. But if you have two systems that is described by the external potential, we will not know if this density is unique. So a proof of uniqueness of the density is needed. That is the Hohenbein and Kohn theorem. The theorem is that state that the Gonse density of a bond system is determined uniquely by the external potential. So there is a proof, but I will skip the proof. Maybe we can come back on it after. And the second theorem is just the variational principle. It said that the density that minimizes the total energy is the exact ground state density. So if you minimize the energy, the density that minimizes this energy is your exact ground state density. So there is also a proof. I will skip this proof. And yeah, to construct the exact ground state energy, there is the so-called the Levy-Lieb constant search formulation, where the minimization is carried out in two steps. First of all, we minimize the universal functional, that is the kinetic energy, and the external, the electron-electron interactions. And after we minimize all of them, so and the Kohn-Sham theorem don't tell us how to construct uh, this universal functional, but there is a framework that's called the Kohn-Sham framework that reduce the many body problem into a non-interacting electrons in effective potential. It means that it neglects entirely, not neglects, but since the electron-electron interaction is the problem, he replaced this interacting problem by the non-interacting problem, but with different potential. So here you can see the Kohn-Sham equation is like a single electron Hamiltonian with this potential that he called the effective potential. And he decomposed the universal functional in as equation 33. This is the non-interacting kinetic energy. The second term is the Hartree. The Hartree, that is the classical Coulomb interaction. And the third term is the what we call the exchange correlation that we don't know how to compute it. And if you do some calculation and you compare with the interacting system, you can find the effective potential as a function of external potential that's defined by equation 34. And since this is a single electron Hamiltonian, the density can be computed by this formula, and the ground state energy is given by equation 36. Actually, this equation are the self-consistent equation, and if you want to solve the Hamiltonian, what you have to do is first to construct the nuclear potential, maybe from Canton Monte Carlo calculation of I don't know, and you guess the density. And if you guess the density, you can calculate the Hartree. By this formula, you can calculate the Hartree term potential and the exchange correlation, and you can compute the effective potential, and you solve. You solve the Hamiltonian for this density, and you calculate the new density, and you do a test. If this density is exactly the density of the interacting system, the problem is solved and you can extract all the properties that you want. If not, you generate new density and you continue the cycle. That is called the self-consistent calculation. So this lead to a Nobel Prize, this construction to water cone, that's like the Kohn-Sham construction, and a hopeful approximation to what, to the exchange correlation term, maybe by the local density the GGA approximation. So this lead to Nobel Prize for water cone. So the Hober model now, the Hober model is like a model Hamiltonian that is actually used to describe strongly correlated systems, and it can be used also to describe the mode metal insulator transition, or maybe the high superconductor corporate. And it's defined as follow. This Hamiltonian is written in second quantization. Actually, there is a derivation from first quantization to second quantization. So, but except this term. So these are the Hopi matrix, the Coulomb integral, and the on-site potential. So yeah, these are the creation and annihilation operator, and these are number operator, and they satisfy the anti-commutation relation 29 and 40. So to solve this Hamiltonian, the method we use is the exact diagonalization, because the total number operator, that's this, and the spin operator commute with Hamiltonian. So we can keep ourselves in a reduced Hilbert space. So in the subspace n equal to 2, we can like compute the matrix of this Hamiltonian in a given basis functions. So the basis function that we construct is given by 42, and the Hamiltonian matrix, after some calculation, you reach this Hamiltonian. Once you have this Hamiltonian, it's easy to solve the problem because the ground state energy is the lowest eigenvalue of this Hamiltonian, and also you can compute the eigenvector, that is the wave function. So we study in this graph the ground state energy as a function of on-site difference potential, as shown in this figure 2, for 2t equal to 1 and for different value of u. One can see that the ground state energy like decrease as a function of delta V, and increase also as a function of, for different value of U, increase with U and decrease with V. So we study also the ground state occupation, the difference between the site occupation as a function of delta V, and the behavior is different, like just the contrary of this one. So yeah, the density functional theory for the Hubbard model, like the Consham Hamiltonian. If you want to get the Consham Hamiltonian, what you need to do is just to neglect the interaction part, that's the U part, and we replace this potential by the Consham potential. So we decompose the total energy. This is the non-interacting kinetic energy, the exchange, the correlation, and this the last term. So this one can be computed exactly, since we can solve exactly this Hamiltonian by exact diagonalizations. We can compute exactly this kinetic energy and this heart rate and change, and given by equation 46. And if we minimize the total energy and we compare with the non-interacting system, the interacting system, we can find the Consham potential given by equation 49. But usually the Consham potential, this potential is the correlation, like is approximate, like I said before, by the local density or maybe some approximation, and we can find the approximate value for the ground state energy. But for our model, we can solve, since we can solve exactly the Hubbard model, we can construct exactly the Consham potential by a self-consistent scheme. This is the program we have developed in Python to compute exactly the Consham potential. I will not lose time, but you can come back on it in questions. So
Yeah,
yeah,
you have only 1 minute, Mr. Kosi.
okay,
So yeah,
sure. Yeah. So with
can
this
go.
Hamiltonian, we can study maybe a given problem in DFT. So we have decided to study the fundamental gap problem that is defined as the difference between the ionization and the affinity. Like we use the Consham consistent scheme to compute all this energy, and we study the gap of the Hubbard dimer as a function of delta V that is given by this curve. And also we study the what we call the derivative discontinuity, like the difference between the true gap and the Consham gap. So in conclusion, what we have done is we analyze the ground state energy and density of the Hubbard dimer as a function of the on-site potential. We have shown that density functional theory works on a lattice for integer particle number by computing self-consistently the Consham potential. And finally, we have shown that the Consham gap can be smaller or larger than the fundamental gap, and the difference is related to the derivative discontinuity of the exchange correlation potential. Okay, thank you.
Thank you, Mr. Kosi, for the presentation. So the floor is now open for questions. So please, in the attendee, just raise your hand if you want to ask a question. So while we are doing this, can I ask Professor Sugoti to just unmute his mic if he can hear me? Okay,
yes,
we have one question from. Okay, thank you so much. We have a question from Professor Afolabi. Yeah, you can talk, Prof. If your mic is muted. Okay.
Oui, c'est ça. Professeur Falabi, you can go. You can ask your question. Oscillation chute. C'est vrai qu'on a des matériels, mais
maybe we can.
I've lowered my hand. I was trying to open the.
avec le fil. Yeah, it's okay, we are hearing you. Il y a aussi quand même des ressorts à boudin. C'est vrai que nous utilisons avec un chronomètre. Mais on n'a pas. We are hearing you. You can ask your question.
There's a noise behind you.
Hello?
So there is noise behind. I can't.
Okay, I think it's fine now. Yeah.
Okay.
Okay.
So
I was trying to open the presentation. So while I was trying to open, the man finished the seminar. So I cannot ask questions since I didn't participate from the beginning.
oh, okay. No, because you raised your hand, so we thought you have a question. Okay,
I can only ask him that these things he did, what are the several areas of applications in a modern day life? Areas of application in modern day life.
Okay.
Yeah. Actually, this is like a theoretical study, like for strongly correlated system, because we know that in describing a strongly correlated system, the approximations available actually don't give like accurate method. So people can try to construct like a model Hamiltonian that can accurately describe a strongly correlated material. And we know that if you can well describe strongly correlated material like LEO or TiO2 that are useful in like solar panel, or maybe for LEO for battery, it can be helpful to predict like batteries properties, or to predict uh, 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 properties of
That is
semiconductors.
what. Yeah. That is what we are interested that you highlight, since application is one of the focus of this our Crepas. I think you understand. So thank you.
Yeah.
So all these strongly correlated systems should be highlighted, and there are examples and how this theoretical development can be applied to them in maybe your further research.
Okay. Thank you, Professor Afolabi. We also have Mr. Aderemi. So there's a noise.
Mr. Aderemi, you can
Please,
talk.
Mr. Aderemi, can you talk? There's a lot of noise.
Mr. Aderemi.
Mr. Aderemi.
Abdul Karim.
Thank you, Mr. Kosi, and that's a wonderful presentation which you have done. But please, I have two. Oh, sorry. Okay. Yeah, I'm talking now. Thank you, Mr. Kosi, for the wonderful presentation. Please, I have two questions to ask. And the questions are firstly, yeah, I'm hearing you and I'm talking. Yes, I'm talking, I'm hearing you. I'm talking.
I'm hearing you too.
Can you go ahead, Mr. Aderemi?
Okay. Yeah, what I'm saying is I'm having two questions to ask Mr. Kosi.
Yeah.
The first question is that what is the software he used for plotting his graphs?
Actually, it's Python.
Okay. The next question, please.
Okay. The next question is that what in his slide, that's slide 22, he mentioned the range of and he talked of a value in which if the Konsham equation is not self-consistently solved. So now I want to ask him that what is the range of value for him to know if it is self-consistently solved or not? Yeah, he used
Like
Python
a
and
range
asked
of
him the range of value at
value of what? Of the density?
I think I think his
Guys, can we?
question was about the fact that what is the criterion of self-consistency? I think that was the question.
Yeah, the criteria is just like the density, the density that we have computed using a fictitious non-interacting consortium system must be equal to the exact density.
Okay, thank you.
Look for instance this one like this one. For instance, this one, like we compute this the delta vk is the difference between the consumption and for the one cycle and the previous cycle. So if this difference is greater than like some a given error, for instance 10 minus 6, or I don't know, there is self-consistency and we can get the density and the potential.
Okay.
Okay.
So next.
So next question, we go to Dr. Awolabi. Please, can you ask your question?
Yeah.
Short
Please,
question.
Mr. Kosi, thank you for the. Can you hear me?
Yeah, I can
Yes,
hear you.
yes. Go ahead.
Yeah. Thank you for a very beautiful presentation. At least, I mean, you have explained the flavor of the work. Thank you very much. My question, because I joined late, which potential did you use? That's the first question.
Oh, actually, I didn't use a software.
I
Everything
mean,
is.
potential.
Yeah, I'm asking your question.
Okay.
It is look, what we have solved is this Hamiltonian, like this one, okay?
Okay.
Yeah, so we didn't use any software like Quantum Espresso or anything like that to use potential or pseudo potential. Everything was coding in Python. So we give a values to this potential V. We like this one, we guess initial values and we can compute everything and we do a self-consistency. Since in our Hamiltonian can be solved exactly. That's the difference between like a software like Quantum Espresso
It means
where
you assume a value for the potential,
yeah
initial value.
we guess initial
Yeah.
values.
Okay.
Yeah.
So
Another
they
thing
did
is that
initial guess.
is there, do you think of a way to harmonize this technique with population-based optimization technique like GA, Getty algorithm, like gravitational search algorithm? Because they can, if we define the search space, I mean, we define the potential value that for the potentials, I mean, the probable value for the potentials. The algorithm can help us to iterate and converge so that you'll be comparing the results with the result of the exactly solved system. And when it converges, then it makes life easy. Do you think of that, or what do you?
Yeah, actually, I am trying to see what you mean. Like you have like a real system, like right, like
Yeah,
and you
yeah.
want to do you want to use this model Hamiltonian to describe it.
No, I'm thinking of just asking, perhaps if it's possible to,
Yeah.
instead of choosing the potentials, because the potential you are choosing initially you will have defined the range of the potential. Some are not some values are not probable at all. You cannot even try them.
Oh, I
Why
know.
some are probable?
Let me tell you, I know your problem. Oh, this is not like we are not describing like a real existing system, like maybe I don't know iron, or like this is just a numerical exercise to prove like one can apply DFT on a lattice. So this we don't have a constraint on the potential.
No
Yeah,
constraint at
but
all.
Yeah.
but I think his question was: is it possible to adapt your code to a real system and make these constraints?
Yeah.
this will be complicated, and it is a hard work. I need to think about that.
Okay. Okay.
Thank you, Mr. Kosi.
Yeah.
So can we maybe move to the next presentation if there's no other question? Okay, so Prof. Sugoti, can you maybe introduce the next talk? And I'll ask Mr. Chebe Kabe, sorry, to maybe share his screen.
It looks like Professor Falabi want to say something. Okay, Professor Falabi, you can talk. You can unmute your.
Yeah. Oh yeah, there's a hand there. So Professor Falabi, yes. Do you have a question?
Mr. Chebekabe, you can share your screen for the moment here. Professor Falabi, you want to ask a question? No. Okay.
Okay, so I will. Okay, I will then invite Prof. Musa Sugoti to introduce the next presenter.
The next presenter.
Yeah.
Okay. Do you hear me?
Yes.
Okay.
Yes.
It's next presenter is Pagdame. Is exact?
Yes, it is exact. Pagdame Tebekabe.
Okay. Are you ready?
Yes, I'm ready. We can start.
Okay. So you can talk about your linear. You talk about linear form in logarithms and mathematical methods of Diophantine equation application in chemistry and physics. So
okay,
you can.
Just for a record, Professor Sugoti, the presentation is 15 minutes.
Oh, 15 minutes, huh?
Yeah.
Okay.
So yeah.
So I can check my 15 minutes.
Yeah, 15 minutes.
That will be sufficient.
Go. You can go now.
Yes, okay. 15 minutes for the presentation and 5 minutes for the questions.
Okay. Then my name is Pagdame Tebekabe. I'm a PhD student in Czech Antioch University. My presentation is on linear form in logarithm and mathematical methods of Diophantine equations, application in chemistry and physics. Okay.
Okay.
Now, the outline of this presentation, we will start by introduction. And after that, we'll give the generalities by defining the naive rate, absolute logarithm rate. And the next, we will give the bounds of n in terms of p. And to finish, we will give the mathematical method of Diophantine equations in physics. And to finish the application in chemistry, but in physics. In physics, that will be, the application is on Kepler third law only, but in chemistry, that will be in balancing equation and to determine the molecular formula. Okay, there we establish the bound of N in terms of P of the following equation. F1 is equal to 2 raised to the power P with NP greater or equal to 0. And there the Fn represents the Fibonacci sequence defined below by F0 is equal to 0, F1 is equal to 1, and the relation between them is Fn plus 1 is equal to Fn plus Fn minus 1 for all n greater or equal to 1. The method we use there is the method of linear form in logarithm, which was introduced by the British mathematician Alan Baker in 1966. We show in this paper how to choose the parameters involving in the determination of the bounds of n in terms of p, and the application of the mathematical method of Diophantine equation in physics and chemistry. Before to give the definition of the generalities, we have to define the Diophantine equation. The Dauphin equation is just simply like an equation in which the coefficients are integers and the solution we want are non-negative. Okay. There, what is the definition of linear recurrent sequences? The linear recurrent sequences is defined like you can see there of order k. If you have it is of the form hn plus k, which is equal to a1 hn plus k minus 1 up to ak hn for all n greater or equal to 0. We assume that in this sequence that the coefficient ak is not equal to 0, it will be different to 0. Otherwise, the sequence satisfy a requirement of will be of order less than k. If all the coefficients belong to z, means uh, the relative integer, all those terms of this sequence will be also an integer. Then we can easily prove by induction that this sequence is an integer for all n greater or equal to 0. Then the following polynomial is called the characteristic polynomial of this sequence. And if we suppose that we can put this characteristic polynomial of this on this form with order of the multiplicity this. Next, the particular case of this recurrent sequence are this when we define an plus 2 is equal to like this with initialization a naught is equal to 0, a1 is equal to 1, and the second bn plus 2, which is equal to also this with initialization b naught is equal to 2 and b1 is equal to a, represent respectively the Fibonacci sequence and the Lucas sequences. Now the knife head, to calculate the knife head of any Dauphin equation or any characteristic polynomial, it is equal to the max of the absolute value of all the coefficients, where this will be the minimal polynomial of gamma, and h gamma is called the knife head of gamma. Next, normally we have this knife head, which is not useful sometimes, but we need to find the absolute knife head. For this, we define the following identity, where gamma e are the roots of the minimal polynomial of gamma, and the absolute logarithm height can be defined below by h of gamma, which is equal to 1 by d log of ad plus the summation from 1 to d of logarithm of the max between 1 and gamma e, which is the usual logarithm absolute height of gamma. Then we will define this proposition we will use later. This inequality is very important for our purpose. Then we define it and we give the proposition, and we have already proved it by induction. Means if you have alpha which is equal to 1 plus the root of 5 by 2 and fn is the Fibonacci sequence, then you have this inequality. Now we will apply to describe the linear form in logarithm and determine the bound of m in terms of p. You have to give the theorem, which is very important. This is the Matveev theorem, which helps us to find this bound we need. And this theorem states that if you have n which is greater or equal to 1, and L is the field of algebraic number of degree d, and gamma 1, eta 1 up to eta L, non-zero element of this field, and we have an integers b1 up to bl, then we define the capital B like a max of all those b I, and the gamma will be put in this form. And we define also the real numbers a1 up to al means ag, which will be greater or equal to the max of d, the absolute logarithm height of gamma g, absolute value of log of gamma e, and 0.16. If you assume that gamma is not equal to 0, then the upper bound will be on this form, means that will be greater than this term you have there. Now further, when this L is real, we have also this upper bound. Then our goal in this section is to obtain the bound of n as a function of p using the linear form of logarithm. From the proposition we give below up, we can obtain this relation pc1 plus 1 will be less than equal to n less than equal to pc1 plus 2, when c1 is a log of 2 by log of alpha, where alpha is 1 plus root square of 5 by 2. In particular, when we take n which is less than equal to 4p, and we replace the Binet formula in the equation 1, and rewriting the above equation and separating the larger term on one side and the smaller term on the other side, and using the fact that beta n is equal to alpha to the power minus n, and the fact that 3 by 8 is less than 1 by the root square of 5, and dividing both sides of the obtained equation by 2 to the power p, we get finally this relation. Then now we have the form, we have all the condition which are, we have all the condition now to apply the Matveev theorem and obtain the bound we need. When we apply it, we obtain this equation. Then now from equation 4, we have this relation, and comparing equation 5 and equation 6, we get this bound we want. Now we can use the previous result which has been done by Peto, which say that if n is greater than 2 and fn is equal to yp, and then p will be less than 5.1 times 10 to the power 17. This case has already been proved by Peto using the linear form of 3 logarithm. And with the help of Mathematica, with those conditions, we finally obtain these bounds. The problem we're trying to solve there is to determine all the perfect powers of Fibonacci sequences. And the condition we will know is that to determine all the perfect powers of Fibonacci sequences, the bound n will be less than 3.8 to the times 10 to the power 13. And there exists a lot of methods which can help us to reduce this bound and finally obtain the exact solution we want. But this is not the, we don't need it in this paper. We just found the upper bound we want. And after this, we will give just the application in physics and chemistry. And next, since we have found this, let's now describe the mathematical method of the D'Enfant equation in physics and chemistry. First, there exists a lot of problems in physics and chemistry, but all those problems are not approachable by this method. To approach this method, to use this method to approach some problem, we need to have, we need to see all the conditions the problem must satisfy to be approachable by this method. Suppose one has an equation in 2 or more unknowns, each having integral coefficient and raised to a positive integral power. One wish to find just integral solution to the equation. Moreover, integral unknowns should make every term integral. In fact, there should then be non-integer anywhere within the equation. If you have a equation of the form like this with all the coefficients integers, this type of equation is called D'Enfant equation of first order. In this section, all the equations are linear, and this result is due to Roger Crocker in 1968. So in balancing equation, suppose we gave the chemical equation of this form, where A1, B1 up to C1 dash are positive integer or 0, and X, Y, X dash, Y dash are the unknowns coefficient of the reactant and product. Then we have this system of equation. And there is one equation of each separate element A, B, C from the given chemical equation. In the reaction expressing the conservation of the number of atoms of that element, each of those equations is D'Enfant equation, since all those coefficients are integral. From this, if we give an example to be more clear, if you suppose we have this given chemical equation X, K, MnO4 plus all this, we will have this system of equation for oxygen. We will have 4x plus 4y plus 2z, which is equal to this. After we reduce this system, we obtain just this simple equation 5x plus 2z is equal to 4w dash, which is the D'Enfant equation in 3 variables. And by inspection, we find the solution x is equal to 1 is 2, z is equal to 1, w dash is equal to 3 is one of corresponding solution on which we will have all the values of all unknowns, which this implies that we have already balanced our equation. We will give this final results. Now, to determine the molecular formula, if we suppose that we have a substance with molecular weight M contain two elements A and B with atomic weight A and B, then for a molecular of the substance containing X atom of A and Y atom of B, we will have this equation, which is already also Dauphin equations. Then, in fact, if IA and IB denote the integer nearest A and B, if we have the difference between A and IA are so small of those elements, then this inequality yields for X reasonably small enough to be found in the molecular. Then we will have, this implies that IAX plus IBY will be equal to IM, where IM is the integer nearest of M. This equation is a Dauphin equation which may be solved easily for X and Y. If we have several sets of positive values of X and Y satisfied 13, one may substitute then in equation 12 and find which one will satisfy this equation, this inequality. This is in this way we can use this mathematical method to determine the molecular formula of a given thing. Now, how to use this mathematical method to solve the Kepler third law? The simplest resolution of Kepler third law is considered as a Dauphin equation relating to circular trajectories of radius r dash and period t dash, which is this equation we know, where A and T are the radius and the period of a singular trajectory respectively. So we will have r dash which will be equal to n square r and t dash which will be equal to n cubed t. The relation between the speed is v dash is equal to v by n. So the invariant will be rv square, which is in the gravitation of two masses m1 and m2 equal to g of m1 plus m2. And moreover, we will have this, which is the quantum condition, which make it possible to determine the privileged trajectories in the Bohr model of the hydrogen atom. Then it is like this. We can also use this this mathematical method to solve the Kepler third law. And when we associate this quantum in a new universal constant, Planck constant, which is the Dauphin equation, which admits now RV as invariant. This is the same Kepler equation, but where the principal exponents are reduced by 1. And this equation is more fundamental because the exponents are identified with the number of dimensions, 2 for the plane of the trajectory, 1 for the time. This is the basis of the single electron cosmology model based on the basic hypothetical trajectory of radius gamma e, which is equal to h bar by mec and the speed mc. And we have this final relation. Thanks for your kind attention. I have done. It is okay.
Thank you, Mr. Pagdame.
Yes.
Yes. Is there any question? Is there any question to the presentation?
Hello, Professor.
Hello.
Yes, Dr. Kona. I want just to ask one question to the presenter.
Okay.
Okay. I want to thank Mr. Pagdame Tibikabe and his colleague for the presentation. It's very great. So the thing I want to know, what is the part of your job? I mean, the differentiating method. Did you create it yourself, or is your part the application of this method in the physics?
Okay. This in this presentation, I have not present our part of contribution.
Yes.
But we have also a contribution in this, but it is not in Kepler third law. It is not in Kepler third law. We have also our contribution, but I have not put it in this presentation.
Okay.
Since it is not already published, is for that I don't put it inside.
Okay. Thank
Yes.
you. It's all.
Thank you.
It's okay?
Yes, it's okay for me.
Okay.
Any question? Is there any question?
If you have a question, just raise your hands. That's all.
Right. But I have a question to Pagdame.
Yes, okay.
Right.
Go ahead.
You give in your presentation an example for chemistry.
Okay.
Can you give another example in physics?
Another example in physics.
Yes, not
For,
chemical equation, but in physics.
The example I gave in physics is the simpler resolution of Kepler-Ted law. But you want another example. This example is not more clear.
This is example.
This example is not more clear in the when we use this mathematical method to solve this Kepler-Ted law. Means the practical example, like in physics.
I want another example.
Okay.
Other than Kepler's law.
Another example other than Kepler's law. Okay.
Voila. Other. Is it?
Yeah.
Is there some example other than Kepler's law?
Yeah, there is a. Well, okay. Actually, the things we know is the application in Kepler-Ted law in physics. But we have found also that there is another example, another application in physics other than this. And the previous question was like this, and I have said that this example we have solved it completely, and it is our contribution, which is not already published. We have it is for those reasons I don't put it. I don't put it.
Okay.
It is for that.
Okay.
You have another example.
Okay,
we found another example.
So you can wait for this publication.
Yeah. It is already done. The paper is already ready. You are just waiting. Yeah.
Okay. Thanks.
No, there's no problem. We are together.
Okay.
Okay.
Maybe the next Crepas.
Maybe next Crepas. Maybe next Crepas.
I want to ask a question.
Yes.
Yes.
I want to ask a question.
Yes.
Dr. Lasheni Shegun-Esan. Yes.
Right, go.
Yeah. From Adekunle University. I want him to give me more information about this Doppler equations to be able to solve molecular weight. I'm using it in solving balancing of an equation.
Yes.
Of course, this is the first time of coming across this kind of an equations to determine the molecular weight, as well using it to balance an equation. Maybe I can have your email.
Yes.
So that I can have a further discussion with you. This is my first time of coming across this equation.
Okay, there is no problem. I have solved many problems. We can use this method to find the molecular formula. Then I can give you my email and we will discuss later. Okay. I will explain you more how to find the inequalities and how to find finally the molecular formula by this method.
Okay.
Okay, there's no problem for that.
Yeah.
Okay.
I'm okay now.
Okay, it is okay.
Yeah, thank you.
Okay.
Also, the organization team, I will add also from the organization team that all the presentation will be shared at the end of the conference.
Yeah.
So please write your emails in the PPT for everybody. So write your email in the PPT or the presentation, the presentation materials, PPT and PDF will be shared at the end of the presentation. Thank you.
Then please, Mr. Dute, you can give my
Yeah.
email to the previous for the person who asked for it. Yeah.
Of course, yeah, no problem. So, Professor Sugoti, if there is no other presentation, I think we can go on the next, right? Professor Sugoti.
Okay, yeah.
Yeah. If there is no other presentation, we can go on. You can go ahead to the next.
Okay, the next presentation.
Okay, thank you, Mr. Chebekabe. And
thank you, Mr. Dame.
Thanks, Crepas, for all. And we are together. Let's see us in the next.
Very interesting presentation.
Okay. Okay.
Mr. Kolani.
Kolani is ready.
We lost him.
Is Kolani ready?
We lost him. He was here, but actually I cannot see him anymore. I don't know. Mr. Kolani is not there. Did Dr. Muzubi can take his place, please? Dr. Muzubi, can you make your presentation now, if possible, because Dr. Kolani, Mr. Kolani is not there. Dr. Muzubi.
Dr. Kolani is not, sir?
No.
Yes, Muzubi is here.
Yeah, Dr. Muzubi, please. Can you make your presentation now?
Yes, I can try. I have a bad internet, but
don't try. Don't try to make it.
Let me share the screen. Coming.
Yeah. So I'll let.
Going to present.
Is Dr. Muzovi, the first presenter in the schedule. He was absent in the beginning.
Dr.
Kosi Amuzubi, the first presenter in the schedule. At 9 a.m. You have the schedule with you?
Yes, I was a bit late. But okay. Let me share my screen now.
Professor Sugoti?
Yeah?
Hi, everyone.
Dr. Kosi is ready?
Yes, I'm ready.
You are ready?
Yeah.
Okay.
Share your screen.
You have 15 minutes also.
Okay.
Present.
Thanks for that.
So you can go.
Yeah, I'm trying to share my screen. Share. Can you see it?
Share your screen. Okay.
Yeah, it's okay. We can see
it. Full screen. Can you see it?
We can see your screen. It's okay. You can go on.
Okay. Thank you, everyone. In this work, I will try to explain a method called Hartree-Plus exchange approximation that we use to calculate the correlation energy for a one-dimensional lattice. And to do that, we use the Hubbard Hamiltonian to describe the physics along the lattice. Okay, so DFT or density functional theory is used to calculate the electron structures of materials and so on. And the main, the key elements or the key components of density functional theory is the use of the density of the quantum mechanics system. Since the density is the key element, all the other properties are expressed in terms of that density. So they become functional of the density. So here what we did is to perform what they call a quotient DFT to calculate the quotient potential and get the correlation energy. Then we use the Hartree plus exchange approximation and the LDA approximation to get the same quotient potential and derive the correlation energy. And finally, I will try to compare the result from the two methods. So in general, we have a system of particles. Here, the particles, they move in a, let's say, space, and they have some configuration, and that configuration change or evolve with time. And because they are all together, they develop a kind of correlation, or they develop a correlation between each one of them. So if you consider cars here, you know that cars avoid to collide, which means there will be a correlation between them to avoid that those cars have these kind of situations where we have crashes and so on. So the point in this slide is to show that once those particles are all together, then there will be correlations among them, and those correlations have names. So you have the what we call the correlation energy itself, and also have the Hartree plus exchange correlation and so on. So now let's come back to our problem. So once you have the system, the quantum system, then it can be described by an Hamiltonian. There's an Hamiltonian that accurately describes that system, but is not known in all the situations. Okay, and here we assume that we have a hand on that Hamiltonian so that we can use it to have exact values of some of the properties of the quantum system, and then compare that with the approximation will perform on the system. So here the system is described by H, and this H is the Hamiltonian, and it contains the kinetic
Hello? Hello?
Hi, we are there.
I think.
Hello, am I back?
Hello, yeah. Not yet. Yes, we can hear you, but yeah, yes.
The screen, yeah, it has stopped. So
It's a
okay.
connection problem, right?
Yes.
Okay.
Can I see it now?
Yeah, it's back.
So I was here. So I said T represents, if you look at the annihilation in the expression of T, it's ended by C dagger, that's the creation, and then C, that is the annihilation. So you destroy a particle on site I with spin sigma, and then you create it on site J with spin sigma, and that shows the motion of one particle from site I to site J. So I'm talking about psi because we are along a lattice. So on a lattice, just like a one-dimensional lattice is like a line that has a site where particles can sit or can be located. So we have U that represent the interactions, Ni up that up arrow represents spin up particle, and then the down arrow represents spin down particle. So these just consider the correlation of two particles of different spin sitting on the same side, and here these sides I, and then you sum over all the sides. And finally, you have the external potential, which is defined by VI. So VI is the potential at site I. So here now we adopted the Hamiltonian, this is the Hubbard Hamiltonian that describes the quantum system. Now, the goal for doing this is to be able to get the wave function. The goal of doing this is to be able to get the wave function of the system. And from the wave function, then you can define the density, the distribution of the electrons along the lattice. Please, can you see my mouse? Hello, can you see my mouse? Okay, I'll continue. And then from the wave function, you have the density and the total energy E naught. So now, how do we get all this if we don't even know the Hamiltonian that represents your quantum system? To be able to do that, Kohn developed a technique that consider an Hamiltonian defined by a fixture, a Hamiltonian on a fixture system, and V superscript Ks is the Kohn potential. And for this method to work, you need to know the density of your initial system. You need to know how the electrons are align along your lattice. So once you have the knowledge of that density, then you can run, or you can perform the Kohn DFT to get the Kohn wave function here represented by phi, and the Kohn potential V Ks. So with this, you can define the different energy of the system, the kinetic energy, the external potential energy. We can define the Hartree-Fock exchange energy, which will be the product, the average of the Kohn wave function and the interaction term. And now you can try to compute the correlation energy, which will be the difference between the exact total energy and the consecutive energies that were computed earlier, like the kinetic, the Hartree-Fock exchange, then the external potential energy. So the problem here is like you can compute all those energy except the exact one that we don't know. So there is a need. This slide, I should have removed it. So forget about this slide. Now, this is the next one. So if you use the Kohn potential and knowing the distribution of the electrons, you can approximate some of those energies. Now, the Hartree-Fock exchange approximation is different from the Kohn approximation or the Kocham method. In this approximation, you need to know the parameters, some of those parameters, and then you use them to approximate the wave function of the whole system. Here, the whole idea is based on the fact that if you have the Kocham potential, then it's going to be the correlation potential plus the Hartree potential, the exchange, and then the external potentials. But we don't have knowledge of the correlation potential. So here we assume that the correlation potential is negligible in the expressions, so that we can approximate the Kocham potential with the Hartree plus exchange potential and then the external potential. Doing that, we can develop, or we develop self-consistent approximations based on these assumptions. And with that, you start with an initial potential, then you do an exact diagonalization to get the wave function, and then you compute the Hartree plus exchange energy and potential. You use them to compute the next Kocham potential, and then come back to the start point and redo again the exact diagonalization, and so on, so that at the end, when your system will converge, then you know that the final potential is your approximate Kocham potential. So we did that, and then we also computed the different energy. Like you have this one now, this kinetic energy is from the Hartree plus exchange approximation. You have the external potential energy and Hartree plus exchange in this case. And then if you want to get the correlation energy, then you need to know the exact total energy and subtract all these summations from it. So now, the next step now, since we know the exact energy for our model, because we defined the Hamiltonian from the beginning, then we want to see how good will be the correlation from the Hartree plus exchange approximation and from the LDA approximations. And here, the first graph show the variation of the total energy, the summation of the kinetic and Hartree plus exchange and external potential energy approximated by the Hartree plus exchange energy, and that's the blue. And then the total energy obtained from the exact system, or from the exact Hamiltonian, that's the red. And then you can see here the gap between them. So we approximated the total energy, but there's something missing. The portion that is missing is the correlation energy. And that portion is the one plotted on the right graph. So the blue is the approximation from the Hartree plus exchange, and then the red is the exact one. But these are the correlation energy, not the total, as it's if you see along the y-axis, it's again written E0 and E0 in blue and in red, but it should be EC and EC tilde. So we have computed the correlation energy from the Hartree plus exchange approximation here. Then the next step is to compute the same thing for the LDA, and then finally compare the two results. So for the LDA, we use two different approaches. The first one is a direct LDA, where you consider that you have a, okay, here we are using fractional particle numbers. So we assume that the number of particles can be fractions, and that's J. And if it's a fraction, then you can still get the distribution row of each one of them. So in the first approximation, we just use the distribution for one fraction. But in the first one, we use an ensemble technique to interpolate between integer particle numbers. So that's the second approach we use for the LDA. And the result is shown on this graph. So the green is the exact LDA, and then the black is the interpolation between two integer particle numbers. So now we compare all the results, or we plot all the results in one graph so that we can see the difference between them. And we did this for different value of mu naught. So here mu naught is 0.2. Okay, and you can see the difference between the two approximations. And here mu naught is 0.8. Mu naught is 1.4. And in all this, you can see that the blue is a better approximation of the exact correlation energy that we define here. And though we can see that the exact is disconnected at integer particle numbers. Like if you look at n is equal to 2, this vertical line, you see that the red is not connected. Okay, it's disconnected. So the method, though it's better here, but it's failed to capture that property of the correlation energy at integer particle numbers. So this is something we have to improve. So all that result, this for 2. Now the next step and what we did was to see how one can move from the approximations to the exact values. If you manage to get the Cocham wave function and you manage to get,
Please,
the
Dr.
exchange.
Professor Sugeti, please, are you checking the time?
No.
Professor Sugeti.
Okay. Okay. Let me finish. Okay. Do I still have time or it's over? Hello? Can I continue? Give me 1 minute to finish.
Okay, continue.
Okay, so I'm hello. I'm saying we work out a method that take the approximate result to the exact result, and you use some factors called Jastrow factors. So I can stop here. So in this work, we use the Hartree exchange to approximate the correlation energy, and then we compare the result with the LDA LDA approximation. Thank you.
Okay, thank you. I am sorry I was disconnected momentarily. Hello?
Okay.
Okay, then.
My connection is not very well.
So you have two connection problem in the internet one.
I have to go to my phone and to go back to my my laptop.
Okay.
This is why with my phone I cannot speak because but I can stop one now.
Okay.
Okay. Any question?
So we have two. Yeah, there is Dr. Larimu who wants a question. 1 minute. Yes, it's okay. Dr. Larimu, you can talk.
Sir. Yeah, Dr. Kosi, you are trying to give us how you can, from the approximation result to the actual result, but they didn't allow you to finish. Please, can you just give us a brief how you can move from the approximation result to the actual result? Thank you. Can you get me?
Okay. Yes.
Can you get me, please?
I'm trying to come back. Okay, so you are talking about this last step.
Yes. You are trying to give us how you can from the approximation result to give to the actual, but I think because of time you try to brush that over.
Maybe I can show you a slide that can explain it to you better.
Okay.
Please be a little quick, Dr. Kosi.
Yes. I just want to explain this last one. Okay, what we did is we use an operator. Then let me share this screen. Can you see my screen? Can you see my screen, please?
Yes.
I hope so, right?
We can see.
We use this operator. This operator J is what I was calling just row factors. The factors are inside the exponential. So we use these operators, and based on the basis of the system, we were able to get the exact value of that operator. Okay, so that's roughly what we did. It's a long process, but we were able to, like here now, we were able to get some values of it and then compute it and try to find a numerical way to get that value. Okay, so roughly that's what we are trying to do here.
Okay.
So it's a long process.
Okay, thank you. Another question from Dr. Goseme. I'm coming. Okay, you can ask your question, Goseme. Goseme, you can ask your question. Okay.
Hello.
Yeah, we're getting you.
Okay. Thank you, Dr. Kosi, for your presentation. I want to have a more explanation on slide 3. Slide 3. Dr. Kosi?
Yes.
He's hearing you.
Slide 3, right?
No, it's slide 3. No.
This is slide 8.
It's slide 3, right?
Yeah, this is slide 8. You are at slide 8.
It's 3.
Yeah.
No. Yes. The meaning of NI in your Hamiltonian. You.
Okay. You want me to explain the NI, those elements inside the Hamiltonian?
Yes.
Okay. So this is the second quantization, right? So you have what we call the annihilation and the creation operator. The annihilation operator will locate a particle at a position and then go to destroy that particle. That's the annihilation. So the C without dagger, the C without dagger, the CI sigma, will go to a site I, and then if there is a particle of spin sigma there, it's going to destroy it. Then you remove that particle from your system. Okay, the particle is no more at that site. Now, the dagger do the opposite. The dagger will go to the site and put a particle of spin sigma there. One remove, one create. So that's why one is the annihilation and the second one is the creation. Now, the way you combine them will capture a property or something related to your particles. Now, if you look at the capital T, the kinetic energy operator or the motion operator, you first have CI dagger, which is going to destroy, and then CJ. Am I back?
Hello.
Sorry.
Yes, you are back.
So I was saying the CI sigma will go and remove a particle, the particle at site I with spin sigma, and then the C dagger J sigma will come to site J and put a particle of spin sigma. So which means a particle which was at a site I was moved to that site to a site J. Once you have a conservation of the spin, then you can think that that particle was removed from site I and then put on site J. So that's the meaning of the first product here. Now the Ni sigma, if you look at this part, is a product of the.
Hello.
It's the same here. It's like, but you destroy at site I and then you create at site I, which means you just localize a particle at site I. If you destroy, then you put it back. So it means you know that there is that particle at that site. Then the way you combine them to define the U term is showing that you have two particles on site I with different spin. One is up and one is down. Okay. If that condition is satisfied, then there will be a contribution from that side in the calculation of the U term.
Okay, thank you. I understand the principle. I have two more questions. On slide 4.
Can go a little quick, please.
On slide 4.
The internet is bad. Slide 4.
Yes.
Yes. Which one? This one or?
The
all
one.
4. Yes. Please, can you tell me which one?
Oh, no, the slide on which you perform the numerical calculation of the Hamiltonian. Dr. Kosi.
Hello.
Hello.
Are you hearing me?
No, I can't hear you. My internet is not stable.
Okay, I think if it's possible,
it's better now.
If it's possible, Dr. Goseme, can you keep your questions for the lunch break?
Okay.
Kosi, can you be with us at the lunch break at 12 p.m.?
At
at 12 p.m., will you be with us so that August can ask his questions during the lunch break?
I'm not sure. I have to go somewhere.
Okay. Bon, my question is small. Dr. Kosi, I want to know what is the convergence criteria you are used to perform the calculation.
Sorry, I did not hear the end of the question. Maybe can you tap it? Or
what is the convergence?
His question was the convergence criterion you are using.
Yes.
Convergence.
Conversion.
Convergence criterion. Le critère de convergence.
Oui, le critère de convergence que tu as utilisé pour le calcul de la méthodologie.
Dr. Muzivi. Okay, I think we have a connection problem with him. Dr. Koseme, you can contact him by email after and try to.
Yeah. Yes, thank you for your.
Yeah. Okay. Thank you, Dr. Muzivi. We will have 10 minutes of break, okay? And then we ask Dr. Lawson, who is not still there. I'm not seeing him in the participants.
My internet is not good. Sorry.
I will ask Ms. Benimana to prepare herself, okay, to start the session. And he will be followed by Mr. Dimo Pangio and Mr. Aderemi. And after Mr. Aderemi, it will be Dr. Aremoa. And then I hope until there, Dr. Lawson will be back. So we have 10 minutes break. So I think between this 10 minutes of break, if Dr. Kosivi Amuzuvi want to ask to answer the questions of Dr. Agoseme, it's okay. But it's a break now. You can go on if you want. Yeah, Professor Suguti, you can go on. I think you have something to say.
I want to know what can I do because my connection is not stable.
Okay.
Can I what if I move from this?
Actually, you are connected on two platforms. Is that?
But because I use my phone to have connection.
Okay.
I use my phone to have connection shows that sometime I lost connection with my.
But you are connected. Okay, I think you can connect yourself directly with your phone. It will be better.
It will be better.
Yeah. So you can switch off your connection with the laptop because sometimes when sharing, the phone is how you say it?
It's disconnect.
So use directly your phone. So click on the link on your phone, and you can use it directly and to use to be connected. I think it's better.
Okay, d'accord. Thanks.
You're welcome. So, Mr. Abdul Karim Aderemi, are you hearing me? Aderemi?
Yes, I'm hearing you. You just unmute my mic now, so I'm able to hear you.
Yeah, you are back
I'm yet
now.
to be able to share my screen.
No, it's not your turn now. Okay. I think you are connected on two different device, right? Mr. Deremy.
Yes.
You are connected to two devices.
Yes.
Yeah, please switch off one, because actually when I promote you in the panelist, I have one Abdul Karim in the panelist and another Abdul Karim in the attendees. So I don't know which one to promote.
Okay, I've disconnected one now.
Okay. So
I've disconnected one. Now maybe you should not.
Okay, yeah, yes, I can see it that you disconnected one. So I will promote this one on which we are talking to the panelists now. So normally you should get us. Okay, I think you are promoted now.
Promoted. Yes, I've seen it.
Okay, good. But it's not your turn. It's firstly it's Miss Benny Mana who will be the first presenter, followed by Mr. Dimo Panjo, and after both it will be you. Okay.
No problem. Okay.
Okay. Good. So if you have some questions on the last presenters, you can go on, because it's we still have I think 4 minutes of break. Okay. I think we can go on. Is it okay for everybody? Hello?
Yeah, it's okay for me.
Okay. We still don't have Dr. Lawson with us, right? Dr. Lawson, are you with us? No. Okay. Did one of you know Dr. Lawson? Hello?
Hello.
Hello, yes.
Maybe you can move to the next.
Yeah. I think we'll move to the next. So, Miss Benimana, is it okay? Can we start? Miss Marie-Laetitia Benimana.
The mic is muted.
Yeah. Okay.
Yeah.
Welcome. Yes, you can talk. Your mic is unmuted now. You can talk.
Hello?
Hello, yes, we can hear you.
Okay. Hi, everyone.
Hi. You can
I'm Laetitia.
yeah, you can share your screen.
I thought I did.
No, not yet.
Okay.
Good. Yeah.
Is it share? Okay. I'm Marie-Laetitia Benimana from African Institute of Mathematical Sciences, EMS Rwanda. It's my privilege to be part of this conference. So I'll be talking about superlearning approach to predict diabetes, stacking KNN, naive Bayes, decision tree, support vector machine, and logistic regression. This work was done under the supervision of Dr. Kosi, Dr. Bourgeois, and Dr. Olwase.
Please, can you go on presentation mode? Yeah, great.
Sure.
Yeah. So.
Okay, that is outlines that I'll be talking on. I'll be focusing on introduction, motivation, methodology, result, and conclusion. Before I wanted to give an overview of diabetes. Diabetes, or the one known as diabetes mellitus, is one of chronic diseases which is caused by an increase of sugar in the blood. Do you know that about 422 million people worldwide have diabetes? Unfortunately, 1.6 million deaths are directly attributed to diabetes each year. We have three main types of diabetes, type 1, type 2, and gestational diabetes. I'll be focusing on those two because the gestational is not common as those two, and it's mostly appearing on pregnancy women and can be treated easily. Looking on the graph aside, we have two main types of diabetes. Type 1 diabetes, it cannot be cured. Yes, because mainly its causes or their causes are unknown, and mostly genetics may play a big role. With this type of diabetes, your body cannot create enough insulin, and their treatment is mainly based on injection. Type 2 diabetes, their causes are known like historical genetics, aging, inactivity of your body, obesity, and many more, and can be prevented with lifestyle modification. And the body, with also this type of diabetes, the body cannot create enough insulin or create insulin resistance. Okay, so with all those type of diabetes, they can cause serious issue, health problem issue, and complication. They requires lifestyle and medication supervision. And what you can know about the symptoms, they have like frequent urination, thirst, and blurry vision. That's the overview so that everyone can have like what is really diabetes. You cannot imagine how diabetes places huge burden on health economy. Looking on this graph on the side, it is showing death attributed to diabetes by ages from 20 to 79 old people. You can see that the more you're getting old, you are likely to die with diabetes. So it is showing that the prevalence will increase at the age between 60 and 69. This is mainly because most of the people at this age, they're still working, they don't have time to take care of themselves, and while their age are somehow, we can say that they are old. So when diabetes is not treated, it can affect most of the body organs and complications such as brain health issue, hearing loss, high blood pressure, kidney failure, and many more. I can emphasize that early detection is the primary key for the treatment and can reduce patient health risks. You may be wondering why we work on diabetes, why we are not doctors, someone else, or what was the motivation doing this project? Well, we worked on diabetes because it's one of common diseases which is affecting the vast age range of the people all over the world. Hence, different machine learning algorithms has been developed to enhance this issue. Our goal in this work was to improve previously obtained results by assembling some of the algorithms. In this work, weak learners have been combined to get the best possible learner. So this is the overview of the data set that you have been used. We used the data from Puma Indians diabetes database composed of 768 counts with 7 features. Those 7 features was number of pregnancy, glucose, blood pressure, skin thickness, insulin, BMI, age, and memory. And we have also one outcome column where one was standing for those who have diabetes and 0 those who don't have diabetes. In our data set, we have, like I said, all data set was 768. 500 among them were not having diabetes, while the remaining were having diabetes. This is like the output when we used Python, just screenshot the output to show how the data was looking like. What we did in general is this one. We just, first of all, prepared our data set, including data cleaning of those process. We selected 5 weak learners and fitted them to the training data set. The 5 weak learners that you have been used is Kenya list neighbor, naive Bayes, decision tree, support vector machine, and logistic regression. Their prediction were compared to the correct labels by means of confusion matrix. With confusion matrix, they give us the output with accuracy, precision, recall, F1 score, and the root mean square. You may be wondering why we use all this on all those metrics. Later you see why, because not only accuracy can give the exact result. So we opted to improve this later ones by assembling them into single but a stronger model We therefore choose and fitted Python-based ensemble models. We use Ada Boost, Gradient Boost, and Random Forest. Their performance were also evaluated, and then we come up with the model or Superlana wanted to develop by interchanging similarity of the data. Sorry?
No, go on. We lost the signals somehow. It is fine now.
Hello. Am I audible? Okay, so I was saying that Kennen is one of weak learner that have been used. It actually works in predicting the target label using neighboring class, like finding the gradient distance. This is like the formula of gradient distance. If I can explain a little bit more, for example, I wanted to classify if someone has a diabetes or not. This is the sample of those who have diabetes and this one, those who don't have diabetes. What we did, with Kennen, what it can do is just to create, to calculate the distance from this new item to this, to the class of having diabetes and to the class of not having diabetes. And the one which is near is where it's likely to classify that person. So if it is really close to those which has
Hello.
diabetes, this new person will be classified. Hello?
Hello? Hello?
Oh,
Yes.
Am I audible? Okay,
Yeah,
fine.
we lost.
So,
No, hello. We lost your presentation. You can share it again.
can I share again?
Yeah, there was some connection problem and the presentation shut down.
I don't see where to share now.
It's the same place, the share screen, the green icon.
Okay, fine. I'll just go. Is it shared?
Yeah, it's okay.
Okay, fine. Now, I was saying that if this naive base, why I was standing for target here, what you wanted is just to predict, saying what is the probability that this person is coming from the group, given you know that bias theorem is in independence order, like probability of y given that x is known. It means what is the probability that this one's coming from, for example, diabetic class. So with using this formula, also that's how we can get the naive base and result. I just explained two because of the time. Meanwhile I've used the 5 weak learners. Those are the results that I've got. From this one, you can see we have five weak learners. This is the decision tree, support vector machine, logistic regression, naive base, and k-nearest neighbor. Among the weak learners that have been used, this is arranged in order actually. The data decision tree is the one which has been performing well compelling in other weak learners. In terms of those 5 metrics, accuracy, precision, recall, ref1, and root mean square, you can see that with decision tree has been able to predict the patient at the rate of 70-80%. But with the confusion matrix, it has been showing us that among them, it means that it misclassified 47 patient has been misclassified as false positive. It means they have been classified those patients like.
Oh. Hello.
Yeah, the small connection problem once again. Just give her some time.
Yes.
Miss Benimana, you hear us? No.
Having diabetes, why they don't have. And
yeah. Yeah, please. Yeah,
Hello?
we are back.
Huh?
Yeah. Reshare the screen again. It lost.
It's lost.
Yeah. There is some connection problem between Rwanda and the rest of the world.
Okay.
Great.
Am I back?
Yeah, you are back.
Okay, I was explaining this table. I was now on the point saying that random forest among the ensemble learning has been the first one which is performing well. You can say it has been able to classify patients at the rate of 85%. Oh, internet is unstable. Am I still there? Hello?
Yes, for the moment, you're still there.
Okay. And now it misclassified, it means 15%. So our target, remembering our target was just to minimize the number of people who are being misclassified. So that's why we said, even if it is performing well, I mean, it's not bad, but well you have, you may ending up dying early. Or for example, if they told you you have a diabetes, well, you don't have, they may affect your life in a negative way. So among those weak learners also can see that naive has been the least, or the one which is nowhere not performing well with 68% of accuracy. So with building, as I explained, the super runner that we have developed, it has really improved our list well. What you did well, interchanging the top runner with those super runner nearest neighbors, as we can see that we were, before we were around, the best one was 85. Now we can see that we have around 96. Yes, now 96, which is really improved, and we are now classifying only 5%, which is really improving. So this is the graph showing all this, like all these models, when we are comparing them together, we can see the top 4 balls from the super runners. They have really improved what we really wanted in terms of accuracy, in terms of all metrics in general, in terms of accuracy, precision, recall, and the fun score. You can see that those super runner that you have been developed has really make what you wanted. Oh, those are the differences from information about it, the diabetes. In case you want to read more, you can go through there. And moving quickly to the conclusion, we have seen that early detection of diabetes is the key for the treatment. In this work, various prediction models have been used in predicting diabetes on dataset composed of
Hello.
768 rows with 9 columns. Hello.
Hello.
Yeah. We lost the
Yes.
audio for a minute, but it's okay. You can finish your.
Am I audible now so that I can come again?
No, it's okay. We can see your sharing.
Okay, fine. I was saying to use those wiki learners to build a super learner and build in ensemble models like random forest, gradient boosting, and other boosts. From the research, we have seen that each model was evaluated based on 5 metrics. And to avoid misclassification, we have built up our super runners. And the research did show us that these optimal classifiers have been improved, the classifier ability to predict diabetes. So this proposed method managed what we wanted. Actually, we wanted to minimize the people who were, or the patients who were being misclassified. And you have coming up with only misclassifying 4% of our patients. So to take this project further, I would recommend doing the superlearner using, as before we have been using the built-in Python built-in other boosts, built-in gradient boosting, built-in random forest. So I would recommend also to use those ones built-in from scratch to see how it can be. So thank you for your time. In case you have a question, feel free to ask.
Well, thank you very much.
Yeah, very, very good presentation. I like it. Thank you, Ms. Benimana. There are 2 hands raised already. So the first one was Alain Dimopandio. So you can talk, Alain Dimopandio.
Okay, thank you for giving me.
Sorry?
It's a answer question answer session. So it's okay. You are following us.
I'm losing your message, please. Can you
Okay. I think you should to make the connection a little better. I will stop your sharing. Yeah. Okay. I stopped your sharing just to. I hope that it will increase a little bit your connection.
Okay, fine.
Yeah. Okay. So it's the questions session now. Okay, you are following us. Miss Benimana, are you following us?
Yes, please, I'm here.
Okay, so Mr. Dimopandio has a question for you.
Okay, thank you for giving me this opportunity. In fact, I would like you to explain more the Q&A, the KNN approach. Please, could you please explain it again?
Okay, fine. Can I share it again, please? Can I share the?
Yeah. You can share it.
Okay.
Are you sharing?
Okay. Yeah. So just take these red ones as the people who have. Hello?
Yeah, we are getting you.
Yeah,
Go
yeah,
Yeah. Yeah, take this rate as the people who have diabetes, and the green, those people don't have diabetes. For example, someone came and he has the features like BMI, like insulin, like all those features that you were working on. So this is the person that I'm talking about, the one who is here. And what this Kenan will do is like we'll be taking each feature actually, like, and then summing up all the distances, and the one, and after summing, and this one we give for each person, like for the new coming person we give, for example, this is, let me take 10% of similarity to this and this one in having diabetes, 20%, 30%, and the one which is really closer is the one which will be, for example, at the end of all the list of the output is seen, we have seen like the one which has a small distance is the, and this one is coming from maybe from diabetic, and this new person will be classified to diabetic class, depending on the result coming from the distance. It means the one with short distances where we classify our new person.
Okay. I hope the connection, there was again some connection problem, but I hope you get a little bit his her answer, Mr. Dimopandio.
In fact, I was just wondering what make her use this approach, since she's talking about diabetes, and I wasn't fine. Since now up to now, I don't know why, what make her use this approach in order to study the diabetes. So this is what I wanted to know, because now
okay, that is that. Hello.
Hello.
Yes.
Yeah.
So now you are asking why I use Kenan in predicting diabetes, right?
Yeah.
So if I can say, if I can go back to my goal, what I wanted is to make the best super runner. I wanted to take just to evaluate different models, different weak learners, because it's just a research. In doing a research, you just take different possibility to see which one is working better according to your goal. So I cannot say why I choose this and this and this. I just took 5 randomly and I just say, let me see which one is working better, because my purpose was just to improve, like to get the best one. So I just take Kenan like the way I take Naive, like the way I can take another, as long as it can give me the result. My purpose was just to compare, to look among the weak learners, nothing else. Thank you.
Okay, great. Thank you.
Yes.
The next question is Abimbola Olaremu. You can talk now. Dr. Olaremu, you can talk.
Hello, okay, thank you. Ms. Maria Benimans, yes, I appreciate your work. I'm not going to talk about the approach for use for your prediction, but my point is, when we're talking about the diabetes, there are so many factors that you need to put into consideration, like your data set was gotten from, your data set, you said you got it from India. Are you on? Can you hear me?
Yes, please. It comes
Yes.
from Indian database.
Yeah, but don't you think the diet of each continent, like the Asia, most of the countries in Asia, they are vegetarian. If you compare that data set with what you obtain if you are using a data set from the United Kingdom, they eat a lot of sugary things like cake, chocolate, and other things. That if you come to Africa, we eat basically starchy foods. Now, don't you think these factors will affect the prediction? So what you have predicted, do you think it can be a universal tool, putting into consideration that these different continents, different countries, our diet varies, and predicting the rate of using this as to predict the rate of diabetes, don't you think it may varies from continent to continent? Do you get my question?
Yes, sure. Thank you for the good question, by the way. You were talking about like the data set because it's for Indian people, that it might not be applicable for all over the world. So that is really a good
Yes.
comment. Yeah, I got your question. So that's really a good comment because when you are starting a research, you have to start from, I cannot say that it can be applicable all over the world because it was the beginning. I wanted to look with this data set, how can it be? Maybe for the next project, I can just improve to see what if for the data set of Africa, data set of actually I used the data set which were available, but in my plans I wanted to I want to make the project further like bigger somehow so that I can exchange the data set to look how good or how it can be performing. First of all, when you are starting the research, you need to have a sample like if it can work here, can it really be applicable on other sides? So this was the beginning actually, and I'm still working. I'm still developing my project for the next time to be applicable. Thank you
Okay.
for the comment.
Thank you. And also, if I can add something, I think if there is some, if you have another data set, you can just relearn your model to the new data set. I think you can make a new learning to your model if you change data sets.
Sure, I will.
Yeah. So the model can be applied to any model, to any data set in case only if you make a new learning to the model each time. Maybe.
Sure, I will welcome you. Thank you.
Okay, there was a question from Ludovic Akona also. Should not forget him because I think he lowered his hand.
Okay, thank you very much. And I have the same question like the person who have talked, who have speak recently. It's about the data set. So
okay,
I'm satisfied. I'm just guessing that perhaps it's because of it's a big data, I think. So because to use this kind of method, you need some big data to fully use this method. I'm guessing, but the question is the same. Thank you very much, Benama, for your presentation.
Okay,
thank you very much.
Yes.
Next question from Dr. Wolabi. You can talk now.
Yeah, thank you for a good presentation. And I thank Dr. Dambi. Can you hear me now?
Yeah,
yes,
we can hear
please.
You. Yeah, although I have one question, one contribution, and let me say 3 contributions.
Okay.
The first contribution regarding the last question of having a data set from Nigeria or from Africa, that does your model, can it work in that area? In a field of machine learning, there are homogeneous model and heterogeneous model. What people do frequently is homogeneous. That is, we take a data set from a particular location to predict the future occurrences of the same location. But it might happen to build a model using features from a location, then you cannot take that model to another location. In machine learning, we don't expect this model to perform at all because it was not trained from the futures. In that case, if it now performed excellently in the new model, then it's a very huge success. Meaning that the essence of this work that the presenter has done is to tell us that these existing models can work, and the presenters has taken a case study of a location. If we want to do the same thing as Dr. Dambi has said, want to do the same thing in another data set, we train, we learn again to acquire the patterns.
Sure.
And then for the first question, the use of KNN. You see, in machine learning, a model cannot perform very well in every situation. Then if you have a problem, we need to test a lot of models. I think that is why the presenter has used KNN, because in the Wika, there are a lot of models in the Wika. You just need to select which model you want to use. I don't think there's specific reasons for our choosing KNN. She chose KNN because KNN is among the models listed in, in the Wika. And then my question, I'm sorry, the root mean square error you presented, because the problem you are solving now, it is a classification problem, not a regression problem. Is it? Is it?
Hello?
I said the question your presentation is classification problem, not a regression problem. Is it?
Yes, it's classification.
In classification problem, how do you calculate root mean square error? Because what is clear to me is that in classification problem, we don't calculate root mean square error. We just plot our confusion matrix from which you can find the correlation coefficient or accuracy or precision. How do you calculate your root mean square error? That's my concern. Do you get my question?
Hello?
Hello, do you get my question?
Your question was in the classification. How
do you
did I
calculate
calculate the root mean square in a classification question, right?
Yeah.
I was explaining you how I have get this root mean square error, right?
Okay. Okay.
I was saying that this root mean square error has been, it's actually the error that made in my classification. So it has been given by the confusion matrix. Like for me, what I did, I used confusion matrix, and with this matrix, and also the root mean square come within confusion matrix. I don't know if I'm clear to you. This root mean square was one matrix in confusion.
Dr. Olabi, is it okay?
Hello?
Okay, we lost Dr. Olabi. Okay, there is another question from Dr. Lubi. It's okay, you can talk. Olubi?
Yes, I'm with you. Can you hear me?
Yeah, we can hear you.
All right. My question has been actually raised by Dr. Ulabi. I was going to talk on the issue of data, Indian data, and then data from Africa, because I don't think she's predicting. The work is more of is a classification. Okay, she's only trying to be able to judge directly this person, the number of people that have diabetes than from those who do not have. It's not like she's trying to predict that this person has diabetes. So I think some of my concerns have been addressed, and I'll just lower my hands now. Thank you.
Okay, okay, great. Thank you.
Yes, yes.
Okay. So everything was very good. Thank you, Ms. Benimana, for being with us and for this beautiful presentation. I will have also one question. It's more a curious question. As I've seen that you are using medical, I don't know how you call it, medical data like weights, things like the pregnancy and all. My question is, these data, did they have been acquired before the moment we know that this person has diabetes? Because if you want to use your model for predicting, that means we should record all this data. For example, in Togo, if you want to implement your model to make prediction, we should record all the data, maybe 1 year. So the question now is how accurate this data could be used if it had been used, I don't know, 1 year before or 2 years before the moment the person will have the diabetes. I don't know if my question is clear. Ms. Benimana?
How accurate your data can be? Yes, please. Hello?
Yeah. My question is the data, because we want to make prediction. So we needed to make a record of some parameters, medical parameters of the. So the question is, if we record these medical parameters earlier, will it be also very accurate to make the prediction? 2 years earlier, for example, I don't know how close to the moment of the diabetes should we be? I don't know if it's clear.
So actually, since the diabetes is long life or long term or chronic disease, as long as someone has, we can say that he has. It's not like other disease, the one which can be cured within 1 year, and someone is no longer have it. So, or for me, what I was just concerned, my concern was that if someone, for example, 1 year, within 1 year, yes, if someone has diabetes last year, probably this year also would be having it. Like, they are mostly accurately, that's how I can say. I was assuming because this one was.
Okay. So in your data, the person already has the diabetes, and you want to predict.
No. Hello?
Yeah, hello, yeah.
I lost you.
Can you hear me?
Okay. Yeah, you were saying in my data set.
Hello. Yeah.
Yes, you were asking in my data set there is what?
Yeah, my question was, first part of the question, what did you predict exactly? Is the fact that the person will have the diabetes, or is the fact that the person can be cured?
Okay, is that the person really have? For me, it's not really prediction. If I can say, I wanted to improve from the previously done. For example, I wanted to build a model that can predict well. Like if someone has a diabetes, does it really this model predict him to have a diabetes? Like I compare what has been in a data set. For example, a teacher in a data set was having a diabetes, right? So I wanted with my model, with all those features, can it really the teacher be classified as diabetes or be classified as non-having diabetes, so that this model can help us in the future for example, for someone who doesn't have a diabetes, to see how accurately this one will be classified correctly.
Yeah. Okay.
Yeah.
Okay, great. So now, if I understand well, my second question is the data that you have, okay, the parameters in the data set. Now, I think you should also think about the fact that what is the longest time of the data set you should have from one person? I don't know if you get my.
How long?
How long
what?
we should record a data from one patient before the prediction can be possible.
Ah, okay.
I don't know if you get my question. It's just it's not a question really, I would say. It's
yeah,
more,
it's like a recommendation or a note.
Yeah,
to
yeah,
take.
it's just some thoughts. Yeah.
Okay.
Okay.
Thank you.
Thank you.
That will be considered. Thank you.
Yeah, you're welcome. So thank you. Next presenter is Mr. Dimo Pangio. So thank you, Mr. Nimana, and we'll go now with the next presenter. Dimo Pangio, you can share your screen.
Okay.
Yeah.
Do you see my screen?
It's coming, yeah.
Coming.
Wow, it's taking so much time to have your screen. Are you in a Focky?
Still waiting for my screen.
Yeah, no, it's okay. It's just come.
Okay.
Yeah, so you have 15 minutes. You can go on.
Okay, thank you. Thank you to everyone for giving me this opportunity to talk about my work. Actually, my name is Jimo Claude. I was born and raised in Cameroon. Now I'm based in France. Actually, I'm a third-year PhD student working on central spin quantum system on the co-direction of Alexandre Faribault and Draghi Karevsky. Okay, so for a small story, the father of one half spin integrable system in my domain is Michel Godin. So Godin is French physicist, which was born on the 2nd December of the year 1931. So, and he is well known for its model, which is Godin model. This model represents a spin which is interacting with many surrounding spin. Okay, so Godin, during the year when he was 25 years old, he joined the CEA. CEA is a research center in Paris. And 2 years after, he joined the group of Bloch. I don't know if you learn about Bloch theory. And when he was 36 years, he passed his PhD in Paris. Okay, so now to continue, I will focus on Godin model. Like I said, this model is the one in which we have a spin, a central spin, which is interacting with the other. So the other spin is called the bat. We have many cases of study. Now, yeah, in the first part of my work, I will focus on diagonal model. So the diagonal model is the one in which the central spin interact along every direction with the others. Okay, so my Hamiltonian have two terms. The first one corresponds to the interaction of the central spin with the other spin in the bat. The second one is the Zeeman effect. which is the interaction of the central spin with a local magnetic field. Okay, so this model have to be integrable in order to find exact solution. Okay, so the model as defined here could be threatened, but if you choose this coupling constant arbitrary, my model will not be integrable. So that to let the model keep its integrability, he has to obey some equation which are known like integrable relation. You know, in classical mechanics, it is simple to describe in an integrable model, an integrable system, because you using the Poisson bracket and the integrable of and integrals of motion. But it is a bit more complicated to do the same in quantum mechanics because we don't know how to describe or to define integrable. We don't know how to define well integrable motion. This is why, by analogy, with the classical mechanics, we transform in the Heisenberg interaction observable in operators and Poisson brackets in commutators. So we propose this relation like integrability equation. So using this integrability equation on my models, I find this equation. The first equation shows how two different spin by their coupling constant. And the second one is what we call the Yang-Baxter equation, which allows how to transform within a position, how three spin can be transformed. Okay. Now, the model, after defining the model, we characterize it. So when working with Gordon models, we have 4 types of classification. The first one is the shift rational one. The second one is the shift trigonometric one. The third one is a non-skew symmetric elliptic. And the fourth is the skew elliptic model. So each model is characterized by the coupling constants in the system. For instance, in the case of shifted rational model, we have the coupling constants which are defined by this way. So we have the coupling following the x direction, which is the same one following the y direction, and the coupling following the z direction is different. It's different from these constants which can be vanished. If we vanish the constant, we return to a model which is fully isotropic. So, but if the constant is not vanished, we obtain a model which is partially anisotropic. As you can see here, all these all these parameters, J and C, have to belong in R, have to belong to N hermetic. Okay, so for the case of shift rational model, we have two situations. The first one is the case where C is 0. In this situation, the model becomes completely isotropic, as I said, and the magnetic field associated to a spin have 3 non-zero components, while keeping integrability in the current model. So in this model, we have the magnetic field here, which can have 3 arbitrary components, but the component have to be, when you choose a component, you can't change their value during the calculation. Okay. So for the case in which C is different from 0, the model become partially anisotropic, and it keeps integrability in such situation. In such situation, magnetic field should have only one component. So we choose the case in which the magnetic field is oriented following the Z direction in order to keep integrability. Since if you change the orientation of magnetic field in such a situation, our system is don't keep the integrability, which is important for the following calculation. What we can notice here is that in this situation, our model always keep the U1 symmetry around the direction of the magnetic field. This is when in this situation, our model always keep U1 symmetry around the direction of the magnetic field. So after this after this model, we have the shifted trigonometric one, in which the coupling constants are different. We can notice here the presence of two homogeneities in the numerators. And what we can also notice is that the value in denominator now has squared. The coupling constants following the Z direction also change. In this situation, we also have two cases. The first one is the one which breaks the U1 symmetry, is the one in which the U1 symmetry can be broken. Here, the local magnetic field depends on the system homogeneity. So here, the local magnetic field associated to each piece of the system, it's not fixed. This local magnetic field can change from one side to another. So in the case where C0 is different from plus minus 1/2, the model have to keep the U1 symmetry in order to conserve its integrability. So in such a situation, we also choose the magnetic field in only one direction. Okay, so after this model, we switch to the non-pure elliptic one. This model can be related to the previous one. So from this model, we can deduce this one. So this model is most larger, and here the magnetic field, as you can see, is completely different, and the coupling constant is fully anisotropic. So here we are in the fully anisotropic system. What we can notice here, like I said, when you take C equals to 0 in the previous case, you switch from those model to this one. Okay. Okay, but once having this parameterization, we wanted to compute the energy spectrum of the model. To do so, there exists an approach, namely the Best-Anza approach, which allow one to compute in such a situation the energy spectrum of the model using some specific algebraic. The problem with this approach is that it leads to solvation of highly nonlinear equation, which allow one to compute some parameters named rapidities, from which we can build the energy spectrum. So seeing this, we try to compute another approach which could be much more easier than the previous one. So the aim of this approach is to use the integrability formalism in order to write our Hamiltonian, like in order to write the square of our Hamiltonian, like a linear combination of the other Hamiltonian. Why doing this? Why using integrability formalism and using parameterization of coupling constants, we opt to these equations which allow one to compute the energy spectrum of the system. What we can do here is that you don't have to know the eigenvalue, the eigenstate of the system in order to compute its energy spectrum. Here we can also get rid of U1 symmetry, which is much more important in the case of algebraic beds answer. Okay, once we compute this spectrum, this energy spectrum, we calculate some physical quantities like the mean value of the spin. Okay, how did we compute this parameter? We use the Hellman-Feynman theorem in order to compute the each local parameter, each local spin following the three direction. Okay. After this, we compute. We choose an example. We take an example and we compute it. We make some simulation using the Newton-Raphson algorithm. Yeah, in this case, what we have is the representation of one state. Yeah, this is the representation of the deformation of one state moving from one initial state in which all spin are oriented in different local direction in order to minimize energy. So yeah, what we can notice is that in the case of when we look to the z direction, we see that from different value of beta, the spin value does not change. The mean value of spin following this direction is not changed. It remains the same. So we move from the case where the spin, we move from the case in which the system is polarized in such a way that the projection of each phase gives the minimum of the energy from a state in which from a different state. In the second case, what we can notice here is that why increasing the value of beta, which is an isotropic parameter, we see that we move from a case where the x spin and the y spin have the same value to the case where this spin have the different value. In this case, this can be interpreted like in this situation we can imagine that the spin when we increase the value of the anisotropy, the spin following the spin in the system has tendency to be aligned following the y direction. Okay, and we can also notice that these parameters are chosen arbitrarily. Okay, so after doing this, we was wondering, since we now after computing this this value, we look for a way to compute the eigenstate using this approach. We compute this. After doing this, we try to compute form factor using the Bert-Ansatz approach. What we can notice in the Bert-Ansatz is that there is a mapping from this approach to what we develop. So there is a way to explain or to compute the rapidities parameter to explain eigenvalue, eigenenergy in the spectrum, like as a function of rapidity. So in this situation, we use the Bert-Ansatz state. In the case of trigonometric model, and we compute some physical, and we compute the Porter scalar of the state with its dual. So doing this, what we obtain is this relation which allow one to compute the scalar product of each state. So we are able to project each state on one another state. Okay, and after this we compute the some physical quantity, some form factors. Like in this situation, we compute the form factor of the rising spin operator, which correspond to the n time n determinant of a given matrix. What we can notice here is that this matrix is could be expressed like in this matrix depend only on the energy of the system. Okay, so once we compute the energy of the system, you use this energy in order to build this matrix and compute this factor form. Okay, after this, we can do the same in the calculation of S minus and SZ. Okay, now, yeah, in this, what you can remark in what I during the previous talk is that in the previous talk, my Hamiltonian wasn't depend on time. So in this case, in this case, we are going to study the dynamics in our model. Why are we going to study this dynamics? In order to predict, to study the behavior of a central spin, which in order to study the behavior of a central spin, which is interactive with another path in time. Okay, so in this situation, we have a new Hamiltonian, which has the same form, but here the difference is that now our magnetic field depends on time. Okay, we can imagine a process like this, in which the central spin has the magnetic field, which is rotating.
Please.
Yes.
Can you please think about the time?
Okay, so how much time do I have, please?
Normally you finish the 15 minutes, but you can try to finish your presentation.
Okay, but I will go rapidly. So in this situation, we use the Floquet theory. We use the Floquet theorem in order to compute, in order to treat this problem. Okay, so to do so, we let our Hamiltonian to become periodic, and we define a unitary operator, namely U, which describe the evolution of the system. U is defined as we know. U is defined in like that. So, but the matter is that in order to keep the periodicity of the system, we introduce new unitary operator, which define in this way. Okay, once we do it, we use the Floquet theory in order to switch from a time dependent basis in a basis in which my system does not depend on time. So we write we have a new Hamiltonian. This Hamiltonian is written in a basis in which our system does not depend on time, and this is called the Floquet Hamiltonian. Once we have this Hamiltonian, this Hamiltonian is the same one that we studied in the first part of the talk. So from this Hamiltonian, one is able to compute the time depending state of the model, some local quantities on some time dependent local quantities like form factors and correlated functions. Okay, after this we did the same in the case where we that term in the Hamiltonian. When adding this term in the Hamiltonian, what happened is that my Hamiltonian is not integrable. So each operator is not longer commuted with the others. But we find a way to to treat this problem by defining a gauge, from this way, and apply the same approach that we used in the previous section. After this, we also study the case in which we can add another coupling constant in which we could be applied in the two direction. Okay, and in order to study the spin orbit effect of such systems. But the approach remains the same, and we compute using integrability relation. We also compute the energy spectrum. Okay, so I think I can stop here. Thank you.
Okay. Thank you. Okay, thank you, Ms. Pandio. The questions, you said there are some questions. Just raise your hand. And please, Mr. Aderemi can prepare himself.
Is there any question?
Any question? No question, okay. Mr. Pandio? Okay.
No, I can stop.
For persons in attendance, yes, you can stop your sharing.
Okay.
For person in attendance, if you want to ask a question, just raise your hands.
Yeah, if you have questions, you just have to let me some. You can write me in box.
Yeah, yes, or you can write a message directly to Ms. Pandio if you have some question.
Okay, thank you.
Okay, so thank you, Mr. Dimo Pandio, for this great presentation. That was very interesting. Now it's turn for Mr. Abdul Rahim Aderemi.
Okay, thank you.
Yeah.
Good afternoon. Hello, good afternoon.
Hello,
yes. Yes.
Can you see my screen?
Yes, you can.
Okay.
You can.
Okay, good.
I can go.
Okay. Good afternoon, everyone. I'm Abdurrahim Aderemi Abdulkarim, and I'm here this afternoon to give an online presentation on a talk that's a theoretical study of the structural and electronic properties of pure cubic zinc blend zinc sulfide. As we can see, this is the overview of what is to be discussed. That's from the introduction and what motivated this research. So we have the methodology down to the results and the conclusion. Yeah, the rapid trend of computational science development made it emerge as one of the most powerful partner to experimental and theoretical studies, and it is one of the fastest growing fields of research in science and engineering. So thereabouts now brings about what motivated this very research, and this research was carried out basically on the wide band gap of zinc sulfide, since it's having numerous applications such as in flat panel display, in sensors, in lasers, optical coatings, infrared windows, and the likes. A lot of work had been done previously on zinc sulfide. Thereby, we have Hinata et al. That worked on zinc sulfide as in 2006. And they carried out the electronic and the optical properties of the zinc monochalogenides using the local density approximation being the full potential linear augmented plane wave plus the local orbiter, as implemented in the Wayne 2K program. Zenebe as well worked in 2012 on the same zinc sulfide alloyed with the manganese and the chromium. So using band, he used band instead of Wayne 2K. Y Sarka et al. In 2014 also worked on the calculation of the structural and thermal properties of zinc sulfide, zinc selenide, and zinc telluride. So using the same thing as that of the Hinata et al., that's the full potential linear augmented plane wave plus the local orbiter. So Bilal et al. As well worked on this same very zinc sulfide. Why Kabita as well worked on the zinc sulfide. So one will now be surprised that why are we having a lot of works being carried out on the zinc sulfide? Yeah, majority of them were working on it simply to get the experimental wide band gap of the zinc sulfide. So while each work was being carried out, there are improvements on the calculated zinc sulfide band gap as compared to the experimental. But yet, there was an underestimation or overestimation of the experimental band gap. And that was one of the main things that now prompted this very research that, okay, what's the problem with the experimental band gap? How can we come in and breach the gap of the overestimation or the underestimation of the calculated band gap? So now that now brings us to the computational details and what we used quantum espresso in this very research. We are having a lot of packages that can be used for the theoretical calculation, such as we have the Abinit, we have the Win2K, we have the Madness, we have Band, we have, and so on and so forth. But Quantum Espresso was basically chosen for this very research, and it's an integrated suite of computer codes for calculations of electronic structure and modeling in materials. Figure 1 is the energy cutoff graph that we got after optimization. It's not possible for us to be working to infinity. So that's why there is going to be a need to optimize our energy cutoff. And that was now what now brought us to this very figure 1. So after being fitted into the program used to plot the graph. Same thing applicable to the K point. It was also optimized to get a certain value which we are going to be using for the subsequent calculations. So why figure 3 is the variation of the energy against the volume. Yeah, before we understand figure 3, I will need to come to equation 1. Equation 1 is the third order Birch-Monagan equation of states, in which both the energy and volume data that were gotten were fitted into in order for us to have our table 3, whereby we are having our lattice parameters. So in table 3, we are having the lattice constant in angstrom, the volume in angstrom cube, we have the bulk modulus in gigapascal, and its spread derivative as well. In this very research, we first of all adopted the exchange correlation function in which we first used was the local density approximation, as seen in table 1, that's the LDA, with the pseudo potential projected augmented wave. That was the pseudo potential that was first adopted in this research. So after our calculation, we discovered that the lattice constant gotten as compared to the experimental lattice constant was being underestimated by about 2%. And I said, oh, wow, 2% is not something that is too much, but can we still improve on and see if we can get a better result? Thereabout, ultrasoft pseudo potential was now later adopted using the same exchange correlation function of the local density approximation, LDA, and it gave a very good result, giving us about 5.4104 angstrom. In comparing these results with the experimental results, we discovered that we are just having about 0.026% overestimation, which was a very good result. So the same thing was done to the PBE. That's another exchange correlation function was used to say, okay, can we still even improve on the results? So using the PBE, we saw that, yeah, there was an improvement, and the improvement was the underestimation now drops from 0.026 to 0.022%. So can we still have a better result? We thereby went further using PBE. So using that, we now got an overestimation of about 0.028%. So thereabout, we stopped the exchange correlation function since we've seen something that is better with that of the PBE. So while we now have the volume, and also we have the bulk modulus here as I'm taking my cursor, we also have the bulk modulus derivative here as well. So that now takes us to the crystal structure, which is shown in figure 4 of zinc sulfide, showing its coordinates as well. So figure 5 is the band gap structure, that's the calculated band gap structure of zinc sulfide using the Pedibrock-Eisenhower, that's the PBE exchange correlation functional with ultra soft pseudo potential, since that was what gave us the best result. Why figure 6 is the band gap calculation of zinc sulfide using meta GGA. Yeah, I'll be coming back to both figure 5 and figure 6, explaining from this my table of table 4. Table 4 is the table showing the band gap calculations for all the pseudo potentials and for the pseudo potential and all the exchange correlation functionals that were being used in this calculation, which is one of the major work of this research. Yeah. LDA, which is the first on the table, using with ultrasound pseudo potential, gave us a band gap of 2.122. In comparison with the experimental band gap, we discovered this underestimated the experimental band gap by about 42.3%. So 42.3% is a whole lot of percentages as an error in our calculation. We then went further using the PBE, that's the Pedibrock-Eisenhower. And using that, we discovered we are even having a more underestimation, which that's about 44.9% underestimation. We went further using the PBE Sol, and that gave us about 43% underestimation. So that is, since all these things are being underestimated, okay, let's try and see if we can use other exchange correlation functionals and see if the result will be better. Thereabout, we employed using GAU PBE, that's the Gaussian PBE and HSE. Using these two exchange correlation functionals, we got a better result. And the better result we got was that we have an improvement in our calculated band gap as compared to the experimental band gap, but yet it underestimated the experimental band gap by about 30%. So then meta GGA was now later employed. And using this, we have an excellent result of around 3.626. In comparison with the experimental band gap, we discovered we are only having about 1.5% maximal error. So from 42% to 44 to 30, now to 1.5% maximal error. So in using this, you now say, oh, this is a good answer, which will now take me back to our figure. In figure 5, as we can see, that zinc sulfide is a direct band gap, but the band gap using the PBE with the ultrasoft pseudo potentials we can see here is underestimated the experimental band gap. And that was what now brought us to using the meta GGA, and in using that, we have an excellent result, which is now an underestimation of about 1.5%. So, and with that, that will now take me to the conclusion that shows that from all what had been discussed earlier, our calculated values of the lattice parameters for zinc sulfide are in excellent agreement with previous theoretical calculations and available experimental data, as shown in table 3. As well, the ultrasound pseudo potential also gave a very good result for the lattice parameters when compared to the projected augmented plane wave, as seen in table 3 as well. While our calculated electronic band structure results obtained using meta GGA was in excellent agreement with available experimental data, as shown in table 4 and in that of figure 6. These are the references, and thank you all for your attention.
Okay,
Hello.
thank you. If there is any question in the attendee, or from the panelists. Questions are now welcome.
Thank you, Abdul Rameni. I'm sorry. I have a question. Hello.
Hello, I'm with you.
Yes.
Oh, yeah. I have a question. Let me know. Can you get some application? Give me some application of the material you study.
Okay. Yeah, it can be used in flat panel display. It can be used in sensors. It can even be used in all these lasers, optical coatings. In fact, it can be is having a wider range of application. Those who are in civil engineering really needs it. Those in metallurgical engineering, those in material science engineering, it's having a wider range of application. It depends on one is trying to use it for. Because a lot of properties were being calculated for this material.
Another question coming.
Okay.
Hello.
I'm with you.
Okay. Is it possible to get easily this material in Africa?
Yes, of course.
Easily?
Yes.
Okay.
Yes, I've answered.
Okay.
Okay.
So, do we have other questions from in the chat? So it looks like you guys have got the topic very well. So thank you, Mr. Abdurakim, for your very nice and interesting presentation.
You're welcome.
So if you have more question to her, just send him a private message, maybe to discuss more. So now we are going to place Mr. I don't think if Mr. Aremia Dr. Isiaka Aremia is with us. Oh, I think there's someone. So
hello, sir. Am I on?
Yeah.
Yeah. So I want to appreciate Mr. Abdul Karim Madiremi for the wonderful presentation. But I think maybe you can send a personal link so that if you want to get in touch with him, because you said you can get in touch with him, so that you can actually communicate with him personally after the presentation.
Okay.
Thank you.
Sure. So, Dr. Isiaka Aremia, are you with us? Okay, it seems like we don't have the next presenter with us. And I can see now Mr. Abdul Karim sent his email. So if for people who are interested, just communicate with him. Okay, so if Mr. Dr. Isiaka Aremia is not around, so I would then close the meeting. But then before I can see Dr. Beltaco is raising his hand. Okay, Dr. Beltaco, the floor is yours.
Hello.
Yes. Yeah.
Hello.
Hello.
Yes, you can hear you.
Yeah, he's trying to connect to internet, Aremoa.
Oh, he's trying to connect. Okay.
Yeah, he's trying to connect to Zoom. So let's say in 2 or 3 minutes, let's say it's not working for him right now.
Okay. Okay, that's fine. So let's so while waiting for Aremia, if someone has any question about the previous presentation, you can ask. The time will wait for Dr. Aremia. Thank you.
Hello.
Yes, Professor. Yeah, props go TV.
Yeah. Is it? Is it ready?
Yeah, yeah, we are still waiting for Dr. Aremia. The time for him to get. So I think we can then maybe put his presentation for the
Hello.
Yeah.
Hello.
Can we
Hello.
put his presentation to the next, like after lunch?
After lunch. Okay, it's okay.
Okay. Because
So
now we
when is
because we have
when is the
already
next start?
we have passed the lunch time by 12 minutes. So
Mhm.
the lunch. So we are going to start at 1.
At 1 p.m.
Yep.
Okay, 40 minutes. 50 minutes. Okay, it's fine. Okay, thank you so much. We'll try to connect to install it before that.
Okay.
Pardon, c'était quoi?
Okay. So let's say thank you to everyone for attending this first part of today's presentations. So just a quick recall. So the next people that will present are Dr. Yawido Jimochon, this is me, Mr. Kayode Dada, Mr. Olausun Abayomi, Mr. Olalekan Adewale. So let's get ready for the next talk. And then we'll have a coffee break. And after that, we'll have Dr. Eric Siki, Mr. Ridwan Apolabi, Mr. Adeyemi Oloruntoba, and then Mr. Emmanuel Faboro. Then before the break, we'll also have Dr. Samialo Azote. So thank you for all, and thank you for attending. So I'm going now to open the mic for all of us. So we are free to talk. We are free to discuss. Okay, see you in 45 minutes, let's say.
Okay.
Hello.
Yeah. Yes.
Dr. Lashini, what about Dr. Lashini? When is he presenting?
Sorry, can you come again?
Dr. Lashini, who is he presenting? I thought I saw him on the list of presenters for today.
Can someone hear? Because I think the network is not good. Maybe you can.
I think he's saying that the next person isn't there.
Oh.
Dr. Lativi Lawson, I think, or am I no?
No, it's Dr. Isiaka Aremia.
Aremia, okay.
Yeah, but he's trying to get connected. So we suggested that we go for lunch, then we'll come back.
Yes,
So
it's good.
after lunch, you can, yeah.
Good.
So if someone knows Mr. Kayode Dada, just tell him we need him.
Ils sont capables de t'entendre.
Quand je vais parler.
Oui, on est capable de t'entendre maintenant.
C'est bon, vous m'entendez? Oui.
Ouais.
Maintenant, comment ils vont voir ma présence?
Oui, on t'entend.
C'est la pause.
Oui, c'est la pause, oui. Tu donnes quoi à manger?
Ah. Vous êtes... comment vous appelez ça? Vous êtes au pays des hommes intègres.
Oui, au pays des hommes.
Ouais, donc les bonnes habitudes voudraient que les hommes intègres s'occupent des hommes qui se cherchent encore.
Des hommes qui se cherchent encore.
Ouais.
Je pense que les hommes intègres cherchent l'intégrité. Hein?
Ah, là, c'est grave.
Ah, c'est pour dire qu'on a vraiment des problèmes.
So, English speaker guys, this is our French time now.
No, yes, our French time.
So please allow us to speak our French a little bit.
There's someone who cannot understand French.
Yeah, in the attentive we have people. Mais c'est pas grave, c'est la pause, c'est le lunch time. Tout est permis.
Ouais, ok.
Oh yeah, I'm getting a question from Prof. Daisy. Yeah, there's no problem. There's no problem. So she was asking if they can post the question in the chat because they are maybe in the place where there's a lot of noise. So Prof, there's no problem. Just post your question in the chat. Then the chairman will be charged, or yeah, will then ask the question for you. And if you are not satisfied, you can still ask. Yeah. But right now your mic is on, so I think you can speak.
Party dollar. Wow. Party dollar. Wow. The one say give me 24 hours. Yeah.
Une présentation, je l'ai bien dit. Good.
Hello. Hello.
Yes.
Okay, good. Il y a quelqu'un qui a du bruit chez lui. Mr. Afolabi Ridwan. Mr. Afolabi Ridwan, please can you switch off your mic?
You are a host, you can do it.
Ah, okay, yeah.
If it's not.
Okay, it's fine now. Okay, so we need to prepare. So Dr. Yaovi Dodimochon is the next one, and after Yaovi Dodimochon, this should be Isiaka Aremoa. And then after Isiaka, it will be Kayode Dada. After that, Obayomi Olausan and Ade Wale Olalekan. So these are the next presenters. So let me make sure everyone is online, or maybe let me know Mr. Mochon is online already.
Excuse me. Hello.
Hello.
Sorry, I just want to ask, is it possible that Mr. Arima starts? If it's possible, I don't know. Since he...
Mr. Who?
If it's possible that Mr. Arima starts, because he is in the last session, so... Then...
Yes, in fact, yes, it was supposed to be like that, but then Doji said something like he has an appointment after that. So
okay,
just have both of them. Yeah.
Okay. Sorry.
That's okay. So Mr. Aremoa is here. So Mr. Doji. So we have our next two presenters, Yaovi Doji and Aremoa. Then can Kayode Dada, is it online now? Kayode Dada from Obafemi Awolowo University, Nigeria. Are you online? Or maybe I can check.
No, I didn't get.
No, he's not there.
He's not there, so
And I cannot see Mr. Latif.
So maybe they are not yet back. At least we have the next two presenter. So let us start, and then we'll see how people will connect next.
Can you see my screen, my presentation?
Let me go to the presentation mode. No, not yet.
Let me stop. Share again.
Okay, so Mr. Dodi Mochon, maybe you can start. You present on cell mechanics in a biomaterial injected therapy for myocardial infarction. Too much technical words, but I guess you explain because yeah. So you have the floor. Just you can start anytime you want.
Can you see this the screen now?
Yes.
Okay. Okay.
So you have 15 minutes for your presentation, and then we'll have the questions section for 5 minutes.
Okay, thank you. Hi again for everyone. So my name is Doti Mochong. I'm going to present the part of my PhD study at the University of Cape Town, and I'm currently at the Department of Human Biology in the Division of Biomedical Engineering. So the title is Cell Mechanics in the Context of a Therapeutic or Biomaterial Injection for Myocardial Infarction. So this is the outline of my presentation. So as a background, myocardial infarction is actually what people usually call heart attack. So this happens when one of the artery is blocked, we'll say. So as you can see here, we have some fat. So it actually prevents the blood to flow through this artery. And the particular artery that is affected is the coronary artery, which actually irrigate or bring blood to the myocardium. So the myocardium is the tissue of the heart. So if this artery get blocked, so what happened is the tissue or the cells that are inside this tissue will die one by one, and then the tissue will be damaged. So as a therapy of heart attack or myocardial infarction, one of the treatment is to give a heart as a transplant, or give some drugs, or go for a surgery by making some reperfusion. So in the research nowadays, there are new approaches that are coming out, because heart transplant is very difficult to actually implement, because you have to queue for someone to donate his heart before, and the drugs actually they did not really work for a long time, and the reperfusion is actually very invasive, and it's not even 100% available and accurate. So in the research, the new approach that have been taught are the injection of biomaterial. So sometimes they add some cells, mainly stem cells. So stem cells are those cells which are able to differentiate into other type of cells. So the idea is, when you inject the biomaterial, which is a kind of which is like a gel, when you inject it in the part of the heart that is damaged, the idea is that if you put cells inside, they will maybe differentiate into cardiac-like cells, not cardiac cells, but then cardiac-like cells. It's like they will behave like cardiac cells. Then they can regenerate and probably get a new life to that part of the heart that is damaged. So here, sorry for the image. I don't know what happened to the readings. It's very hard to read. But the whole idea here is that you collect, so you make a culture of your stem cells. You collect them, and you inject the gel into the part of the heart that is damaged. Then so people have done that like a lot in research, and they have actually observed some improve in terms of the heart functions. But the main problem is most of time or the beginning, what happened is we don't really know what happened to the cells, because this process actually is not really accurate, because sometimes you get, so the cells got lost, or sometimes they die, so it's like unknown. So in order to understand that, our study actually aimed at investigating the mechanics of those cells. So basically, you want to see how those cells feel the deformation. So it's actually well known that deformation, which is a mechanical stimuli, is one of the factors that affect how cell react. And when I say cell react, is mainly by what we call signaling. So it's like they produce some growth factor that will activate a lot of biochemical reactions. So basically, you want to see how the mechanical input will impact that reaction. So to do that, first of all, we develop a biventricular geometry. So this is a heart of a rat. So we got the image, the data from CT scan images. Then we use some software to develop this 3D geometry. Then we actually implement a full cardiac cycle. So it's like the passive filling and then the contraction. So following that, we extract a small block from the region where we actually deliver some biomaterial injected with cells. So we extract that small block because we are more interested in cells. So what we did is that from that block, we theoretically actually include some cells. So here you can see 9 cells that are inside the gel part. So this is the gel part and this is the tissue. And we call this submodel because it's like sub of the big model to be the biventricular model, like the full heart. So now if you zoom a little bit in what happened in the cell, so this is the membrane, this is the cytoplasm, and this is the nucleus. If you guys can remember some few biology classes from high school. So the next step is to develop a finite element-based model of our heart and cells, as well as the biomaterial injected that we put inside the infected tissue. So what we do first is to define the constitutive law. So constitutive law, I would say, is a mathematical representation of the response of any material to some change or some mechanical change in the environment. So it's like if you take a rubber material and you pull it. So we have a mathematical way of representing the response of that rubber material to the load that we apply by pulling. So here we use an approach which is called the strain energy density function approach. So in our case, we use a hyperelastic material with an anisotropic behavior, which means that the heart tissue actually behave differently in the given direction. Then we also need to implement or represent the active contraction, which is the second phase of the heart beating. And we use the time varying elastance approach. So what you need to get here is the T naught actually is the active tension. The active tension is somehow the active electrical signal that the heart is getting. So this is a model of this active tension. Then we actually include it in the heart model together with the passive response to get the active contraction phase. So this is for the tissue. Now, when you come to the biomaterial injected, we use hyper-elastic material, but this time not anisotropic, but isotropic. And the model that we use is called neo-Hookean. So this is the energy density function that is used. So all those parameters, A, B, C, 10, they are actually calibrated. Calibrated means you actually do some experiment, you get experimental value, you do your simulation, and you put some initial parameter in your model, you run it for many times to get optimized. Then the final output will give you those A and Bs. So once you set that, you know your model is not validated, but it's actually calibrated. So I'm not going to actually go in details in
Yes, you have 5 minutes left.
Okay. So I'm not going to go into details of what happened here, but I will just show you the result of what we observe in the cell. So in average, we know that actually the membrane is actually the one that is more deformed, following by the the nucleus and then the cytoplasm. So this information will be used in such a way that when we know the deformation in the cell, we can then guess how or the level of signaling that cell can produce. So this is the histogram that we use for various actually gel stiffness, because what we also did that I didn't say is that we actually vary the stiffness of the biomaterial that we use to also target or to investigate also the effect or the impact of the stiffness of the gel, just to be optimizing the well-designed gel. So those are not the full result, but I'm just showing few results to give you some idea of the impact of the gel. So as you can see here, this is different stiffness of gel increasing. So when you increase the gel stiffness, we found that the deformation actually get less. So which means if we want cell to deform a lot, then we have to use like a very soft gel. So this is the histogram just to show you the range of those values. So in conclusion, I would say that we successfully developed and validate a biventricular model and a sub model that I didn't show here. But then we also get some cell mechanics data, which will allow us, as I said before, to investigate the level of growth factor production. And we also, with this model, can check or find the optimized biomaterial stiffness to be used in treatment for myocardial infarction. So this is one of the experimental data, experimental work that where we start from. So what they did is that they used some like many input as a mechanical input, and they were measuring the level of growth factor that is produced. So what you see here is when you increase the deformation of cells, you have more growth factor that is produced. So we can use this relationship actually to guess or to predict the amount of growth factor that our cell will be producing in the deformation that they are experiencing. So this is all for me, and so this is my team. So I'm somewhere here. So this is my boss with the beards. Thank you.
Yes, thank you, Mr. Doji Mochon, for this nice talk, and you have been in the right time. That's very great. So I saw you are in the same team with Sama Elsher, one of our colleagues. So it's time for questions. So now everyone have the floor for 5 minutes. We'll take like 2 or 3 questions, and then we'll go to the next presenter. So the person who wants to ask a question, just raise your hand, and then we'll allow you to just speak. Ask the question you feel like asking. Okay, time for questions. Hello, guys. Are you listening or?
There is a question on the messages from Dr. Daise.
Okay, on the messages, okay, let me check. Discussion. Okay, is heart attack the same as heart failure? Is a question for Doji. Is heart attack the same as heart failure?
Oh yeah, yeah. It's actually the same. It only depend on people who work. Like in research, we have names. In medical environment, they also have names. So it's the same thing.
Okay, so
heart attack is the last stage.
Sorry, go ahead. Go ahead, please.
Oh yeah, so myocardial infarction is, so I would say myocardial infarction is the process of the damaging of the tissue. Then heart attack is when it happened. Like when you get when you really get injured, and they have to bring you to hospital, or yeah.
Okay.
So all of us, we can be experiencing myocardial infarction without knowing, just because it's just a small piece of scar tissue there.
Mm-hmm. Okay, so is there any other question? Or
one hand is raised.
Which hand is raised?
Click on participant, you said attendees.
Okay, yeah, because I'm only looking at the panelists. What?
Activate is
okay, Obayami. Okay. You can speak now. Obayami Olauson. Can you speak? You have a question?
Mr. Obayomi Olauson.
Are you okay? Before he asked his question, I wanted to know, you said a lot about cell deformation, but my question is, when you inject the thing, I don't know the name, but how sure are you that this actually repair the cell? Like, what is the percentage of success of this injection stuff? Hello.
This is a good question. Yes, hello. Can you hear me?
Yeah, it's fine.
Yeah. Okay. So I'm saying this is a very hard question, because experimentally, even when you inject cells, so at the very beginning, what happens is when they inject cells in the heart, so due to the heart beatings, sometimes they find that the cells will found in the liver, in the lungs, like someone else, like somewhere else.
Mm-hmm.
So that's actually why people really want to know how to design the gel. Will it be stiffer? Will it be softer? Will it be, like the composition? So how to actually design the gel to first keep the cells, and then make them to produce the protective effect that we want at optimum.
Mm-hmm. So in your modelization, can you actually find the right form of this how do you say the right one that you could?
Yeah, so for us, what we found so far is that for a softer gel, we have more protective effect.
Okay.
So now the problem is to know if the cell will not move, because in our model we did not include anything like cell moving, like cell migration, like the gel pushing out cells. We did not actually include all those. We assume the cells to be inside the gel every time.
I see. So thank you so much for this nice talk. I think we will continue the questions after. If someone have another question, you can ask him anytime. You can still reach him by email or by this platform anyway, from individual discussion side. Okay, thank you, Doji Mocho. We'll go to the next presenter now, if you agree, of course. Mr. Dr. Aremua Isiaka, who actually share his presentation on density operator formalism in coherent state basis, physical and mathematical properties. He's from University of Lomé in Togo. Okay, Dr. Aremua Isiaka. Sharing your screen. Okay, you have the floor now. Go ahead. Yes, open.
His microphone is not is muted. Unmute it.
Okay. Hi everybody. C'est bon. C'est à cause de vous. Our topic is on density operator formalism in current state basis, physical and mathematical properties. As background, we have to give some introduction about density operator in quantum mechanics. The thermal density operator, known also as density operator or density matrix, is a key ingredient in quantum mechanics and quantum information. So,
Go ahead. No, mode presentation. F5. Okay.
ça me gêne.
Hello.
So with density operator formula is provided by equation 1 here, and The states Ci denote the different pure states. Pure state in quantum mechanics means the quantum state where we have exact information about the quantum system, and mixed states also means the combination of probabilities of the information about the quantum state of the quantum system. In quantum information, we also use qubits needs for storage or to transport information in quantum information. So the density operator use qubits as quantum states in a appropriate Hilbert space. The density operator must obey some fundamental relation provided here by equation 2 and equation 3. In equation 2, we have the formal expansion of the density operators in the framework of current state. These current states are provided here by the ket labeled by Z. And also we have the P distribution which go with the density operator, and this distribution must be to normalized through the relation tree. Our framework needed to our talk is the set of current state. Current states are usual states defined on a Hilbert space and provided by relation 4. These current states are labeled by complex number Z with Z equal to R exponential E theta, here given by equation 4. These states needs to be normalized through this relation, and the quantity in the denominator here needs to be in go together with the spectrum of the Hamiltonian of the quantum system studied. The current state satisfy a resolution of the identity, which is a completeness relation provided by equation 5. And there are many generalizations of current state in the literature. So you may consult the references given here. We also need to define two quantities. The first one is the Q-Uzumi function needed in quantum information and provided with the current states, which is the matrix element of a density operator in the set of current state provided by equation 6. And this Q-Uzumi function must also be normalized through equation 7. We also provide the trace of the density operator provided by equation 8. In the context of thermodynamic statistics, the density operator must be written through equation 12 here, and the set of current states are provided by equation 13. So the Uzumi distribution is then provided by equation 14. The outline of our talk is provided here. First, we will deal with some preliminaries. Then we first deal with the example of a Hamiltonian operator of an electron in a uniformity field. And then we will deal with the statistical properties of a related SU11 current state construct for this quantum system. After, we will deal with another set of current states construct for photon ardent hypergeometric, and we will deal with statistical behavior. The SU11 algebra is provided by equation 15, and the generator of the SU11 algebra must satisfy the equation 17. Then we may construct a set of current states associated to this algebra by defining first the equation 19, and then the current states are provided here as eigenstates of the generator denoted K minus through equation 21. The expression of these current states are provided by equation 22, where we recognize the gamma function in the denominator. The system of charged quantum particles attracts much researches in the literature, as we will see here. The Hamiltonian is provided by equation 23, where we have the harmonic potential interaction provided by this quantity. The spectrum of this Hamiltonian are provided by equation 24, and the Hilbert space, which is the framework in which we will define the current states, are provided by equation 25. Then after some algebras provided from equation 26 to 28, 29 to 30, the current states corresponding to this model are provided by equation 33. And they satisfied a completeness relation known as the resolution of the identity provided by equation 36. Then we can study the statistical properties of this quantum model. In the literature, there are three types of statistical distribution. The first one is the Poissonian, the second one the super Poissonian, and the last one the sub Poissonian. These three statistical regimes are characterized by a quantity denoted by the Mendel parameter, given here by equation 41. In our model, to compute this quantity, we need to compute the mean values of the number operator. The number operator statistical mean values are provided here by equation 40. Then we obtain that if the modulus of Z is smaller than 1, then the statistical behavior of our states is sub-Poissonian. If it's bigger than 1, we have a Poissonian statistic case. We can also study the thermodynamics of our systems by defining the density operator provided here by equation 44. This density operator must be normalized through equation 47, and its corresponding expression is provided here by equation 48. Then we can compute the analog of the thermal of the mean values in the standard model, here called the thermal or pseudo-thermal expectation values for the number of operators and the square of the number of operators, provided here by equation 15 and 51. Another model we can study the statistical behavior is the current state provided for hypergeometric system. Recall that the hypergeometric equation is provided in the literature by equation 52. Then we can construct the current states attached to this model, and they are denoted by this quantity, and they satisfy a completeness relation or resolution of the identity. Then we can define the normalized density operator related to this model and compute its trace and compute its expression given by equation 56 and 57. here we have expression of a related coherent state and the density operator when we study the case of some set of polynomials. Then we can compute the density operators given by the major G function as a set of special functions in the literature, and provide the thermal expectation of a number operator and its squares corresponding. Then we can compute the Mendel parameter and discuss the statistical behavior of our system. If we obtain the Mendel parameter greater than 0, then we are in the case of super Poissonian statistics. If the Mendel parameter is less than -1 and is greater than -1 and less than 0, then we are in the case of sub-Poissonian statistics. Tu peux me faire quitter ici, je vais montrer un autre truc. Okay. Then we are at the end of our presentation. Thank you for your attention.
Okay, thank you.
Okay, thank you, Dr. Isiaka, for your presentation, and you also have been in time, so that is very great. For now, we still have 5 minutes for questions, so or 6 minutes because we finished 1 minute ahead of time. So we still have 6 minutes for questions. So you are free to ask your questions now. Just raise your hand for those that want to present, those that are in the participant list, and for those that are in panelists, they can just switch on and speak. So, any question to Dr. Isiaka? Okay, I'm waiting for your questions, guys. Okay, let me see. There is a Wallaby. You have a question? Hello. You can switch on your mic.
Hello, Dr. Isiaka.
Yes.
Can you hear me?
Yeah, we can hear you.
Yeah, thank you for a very beautiful presentation. Very interesting. MashaAllah, barakallah fiqh. Yeah, my question is regarding towards the end of the work, you later use Amite and Legenda polynomial. Do you think of other polynomial like Laguerre?
Laguerre polynomial.
Use Laguerre and Amite. Do you think of Legenda polynomial, are we going to arrive at the same solution if we change the polynomial to Legenda type? It was like 37, 38, I think.
Okay. So, Dr. Isiaka, have you had a question?
Yes, yes. Okay, the case of Laguerre polynomials have been also treated in our works, but we don't have more time to expose them here.
Okay.
We have discussed the case of Emit polynomials also, and have similar results as the one we have presented here. And we can also construct some graphs showing the behavior of a Mendel parameter for some different values of complex numbers.
You mean the results are the same, huh? You mean you obtain the same results using different polynomials?
If the result is the same with different polynomials.
Is that
no,
what
the result
said?
is not the same, but we have different behaviors of Mendel parameter from a set of polynomials to another set of polynomials.
You just fit it. You
They are
just fit it
interesting
up.
results.
Okay, thank you.
Okay, thank you, Dr. Awolabi, for your question. So is there any other question to Dr. Isiaka?
From my side, no, actually.
Sorry?
From my side here, no.
Okay. So thank you so much. Then is there any other person who have a question to him on the Laguerre polynomial? Or so I can ask my question directly. So I wanted to know, how do you actually, the idea, is that the main idea is that to actually use the algebra to construct a new Hamiltonian, or what is the, like I'm trying to connect the different pieces, like, okay, you said use Lie algebra, and then from the magnetic
Please,
field you have
excuse me,
Hamiltonian,
excuse me,
and
excuse
you
me.
try to build a new
Excuse
type
me.
of Hamiltonian. Oh yeah.
Dr. Rumwa is in the same room with you, so you have to stop one of your mic.
Yes, of course, of course. So you can listen.
Yeah, okay.
Okay, I will use his own mic. I mean, my question is like, okay, since he's using Lie algebra and he's trying to construct some kind of new type of Hamiltonian when the system is kind of influenced with the magnetic field, and then you consider harmonic potential. I want to know if the idea is just to construct a new Hamiltonian and try to find new solutions to the Schrödinger's equation or something. You see?
Our first idea is to construct density operators for any type of Hamiltonian and see the quantum effects, that is the quantum statistical behavior of a system. And this quantum behavior is governed by the Mendel parameter, for which we construct some graphs and analyze them.
Okay, thank you. Okay, thank you, Dr. Isiaka Remoa. So we'll actually continue the presentations since we spent already the 6 minutes for questions. So just go to the next presenter. If there is no other question, do you have another question? Okay, let's go to the next presenter then. Kayode Dada I can't see him online, but I don't know whether you are inside. Maybe you can just speak and then Kayode Dada. Does anyone in the group know him? Do you know him or no one knows him? Hello? Okay, so Olauson Obayomi, can you present now? Olauson. Olauson. Okay, I will just give you the right to speak because I think you cannot speak here. Olauson Obayomi, okay. Okay, Olauson Obayomi, you can just on your mic now to start. You'll be allowed to share. You also be
Can you hear me now?
Yes.
Okay, I need to share my screen and currently I can't see the place to do that.
Okay, yes, Mr. Isiaka, please can you stop sharing? Wait, stop.
Hello?
Sharing. Okay. Yes, maybe now try to see whether you have share screen. You have a share screen of where you have the mic you have a hand somewhere, and then maybe you have share screen somewhere.
It's not that I have chat, raise and question and answer.
Okay, let me see. Let me see. Maybe we need to promote you as
If he is not in the panelist, he cannot share his screen.
yes, I think we need to promote him as panelist. Okay. Normally now you should have the options. What do you have? You have it?
Yes, I have it now.
Okay, please share your screen.
Okay.
And then Kayode Dada, we don't have him right now. I don't know, from University of Obafemi Awolowo. No one else here have an idea where we can find him?
Do you have it now? Is it up?
Yes, you have it now. Go to share, full screen mode.
Okay.
You have it below. Okay, that's fine as well.
Do you have
Okay,
it now?
so you have the floor. You have 15 minutes for your presentation and then 5 minutes for questions. Go ahead, please.
I'm having 15 minutes, right?
Sorry?
Yeah. I'm Olasun Abayomi Moses, a PhD student of Department of Physics and Engineering Physics of Obafemi
Can you
Awolowo.
please get close to the mic because the sound is a bit low? If you can.
The topic here is comparison of PCXMC and hog dose programs in the calculation of organ and effective dose.
Yeah.
And to start with, I have my introduction. In radiology, organ equivalent dose and effective dose are important for the purpose of dose assessment. However, there are two methods for assessing these doses. We have the direct and indirect measurement. Well, the major challenge with the use of direct method is that it is cumbersome, and that during examinations, when the patient is being irradiated, the patient organ dose cannot be measured directly. And as a result of that, there are mathematical programs or mathematical tools that are used in order to assess this patient organ and effective doses. Different comparison has been made pertaining to these programs. Examples is such of PCXMC and CADO software. We have PCXMC and Diados software. So the essence of this study is to compare the workability of PCSMC and HOGDOS programs for assessing the patient organ equivalent dose and patient effective dose, just as it can be seen. However, examinations were selected for chest AP, chest PA, chest lateral, skull AP, and skull lateral of the Asia region of human body. And to realize these goals, because of the current trend, we were unable to assess machines parameters and some patient parameters. So in order to do that, we make use of parameters that are published in journals, which are seen on this. So we have for chest PA examinations, chest AP examination, we have examination from 1 to 10, and with the KVP, the MAS, and the FSD, which is the focus to source distance, and we have the filtrations of the machine. These parameters were used as the input parameters into the two programs, and by the time these parameters were input into the two programs, the programs automatically generated the effective dose and the patient equivalent dose as well. However, before that was achieved, we need to generate the in-arc ear camera and to find the ESD, because all those make use of ESD, which is the entrance surface dose, while in order to generate that on PCXMC, we can make use of the INAC, or we make use of the MAS value directly. And after the parameters has been inputted, We have the result and the discussions below. The absolute difference between organ dose calculated by PACMC and hog dose for chest AP is seen below. Is seen on this page. We have the absolute difference between the hog dose and for that of PCSMC. Now, for the first examination, we notice that there is none of the there is none of the absolute difference that gives a value that is up to 1 millisievert. However, for breast woman, the bolded column is shown with 1.77 for chest AP. And so for all the chest AP examination, it is only the breast, which is the organ considered here, one of the organ considered that shows an absolute difference that exceeds 1 millisievert. We also have for chest PA and chest lateral. And for chest PA, there is none of the absolute difference that shows a value that exceeds 1 millisievert. However, for liver, we have 1.19, which exceeds 1 millisievert. Now, when we look for that, or when we find out of skull AP, we find two organs, that is thyroid and brain, showing an absolute difference that exceeds 1 millisievert. That is 1.58 for thyroid and 1.01 for brain. However, for skull lateral, there is no any organ absolute difference that exceeds 1 millisievert. Now, the next thing that we do is that we find the mean value of the organ for each of the examination. And for chest AP examination, we have the mean value and the spread of the standard error of the mean on this page for chest AP. We find the same thing for chest PA, the chest PA examination, the chest lateral 2, skull AP, and skull lateral 1 examination. One of the interesting thing about this comparison is that the comparison between mean organ dose, equivalent dose of PCMC and hog dose, we did a data analysis using a t-test PF for mean value for the main organ doses. And we find out that the p-value here is not up to the difference we are having. All are greater than 0.01, because for the analysis, we make use of 0.01 confidence level. And with that, we realize that for all the chest AP examination, chest PA, chest lateral, skull AP, and skull lateral, there is none of the p-value that is lesser than the confidence interval. And looking for the comparison between effective dose and calculated by PCMC and hog dose, the absolute difference for the effective dose, we have it for the PCMC, the absolute dose, there is one that exceeds 1 millisievert. However, for the percentage deviation between the two programs, we find out that for skull AP examination, that's where we have an highest value of 68.76% difference. However, other ranges from minus 10.55, which is the examination for chest AP number 8 examination. It ranges, we have minus 10.55 to 9.59. To discuss about what has been seen, we have that aside for breast with 1.77 millisievert for chest AP examination in number 1, and liver, which shows an absolute difference of 1.19 for the examination, we find out that one of the reasons for having that is because of difference in the organ that is used to simulate, the organ material that is used to simulate the phantom that was used by PCSMC and hog dose program. So once there is a variation in the material that is used in order to simulate the phantom material, it is expected that we have some variations. However, we notice that there is none that exceed 1 millisievert aside what we have in breast, liver, thyroid, as well as brain. And the reason for that has been seen to be because of the difference in the material that is used for the simulation. And one more thing about that is that there are approximately 2% of those that have difference of 1 millisievert, while the other ones that are not up to 1 millisievert are 80%. And for chest AP, for all the examination that were considered using the t-test, peer 2 sample for means data analysis, and 0.01 significance level, we find out that all these, the p-value there are greater than 0.01, which is the significance level. And as a result of that, it means that there is no significant difference between the mean of the organ equivalent dose of PCSMC and all those programs. Now, on the comparison of the effective dose, similar things was seen, that the results were not up to 1 millisievert. However, the percentage difference as well can be seen to exceed to be a deviation of 68.76% only for one of the examination, while other varies up to that. And as a result of that, we realize that one of the reasons could be because of the anatomical differences for skull AP that is used in the simulation of the two programs, mathematical phantoms. And so in conclusion, because of what we have seen from the study, for the examination of the axial region of the body, in most cases, 98%, the organ equivalent dose calculated by the two programs agree with absolute difference that is less than 1 millisievert. The study also showed no significant difference in the mean of the organ equivalent dose evaluated by the two programs using t-test peer 2 sample for means data analysis with 0.01 significance level. While the comparison of the effective dose, we have a range of minus 10.55% to 9.59%.
Yes, sir.
And so we conclude that there is a reasonable PCSMC are not good.
It's your mic.
Hello, sir.
Okay, mettez il normalement. Moi, America le funa.
Hello, sir.
Yeah, go ahead, please.
Okay.
Go ahead, please.
And so we conclude that the two programs can be used effectively for evaluating effective and organ equivalent doses in conventional X-ray radiological examination. Thank you all for listening.
Okay, thank you so much, Olauson Abayomi, for your nice presentation, and you have also finished ahead of time, and that is very great. So we'll have more time for questions. So I open the floor now for questions, and I already see Dr. Olabi raising his hand. So you have the floor. You can just ask your question directly.
Yeah. Thank you, Mr. Dioshun, for the nice presentation. You compare, can you hear me?
Yes, I can hear you.
Yeah. You compare two methods.
Yes, sir.
Through which you can determine the
Dr.
dose.
Olabi, can you just...
Okay. Yeah. You compared two methods. And at the end of your conclusion,
okay,
you concluded that both methods, they are the same thing. They can be used interchangeably. Either use first one or use the org dose.
Yes, sir.
Can you in the market? In the market, what is the price? I said in the market.
Okay.
Based on the cost implication, which one is better? For example, now, instead of, can you hear me? Can you hear me? Can you?
Yeah.
Me?
You are muted.
Oh, why?
Yeah. Okay. Yeah. No, I think because there was some noise behind and I muted him. So I'm asking him to reactivate his mic now.
Okay.
But I think he's not.
So, Abayomi, can you
Can
hear
hear
us?
me now?
Yeah.
Yeah.
Okay.
Mr. Bayomi, can you tell us the cost implication of the two programs? For example, now, if I have a lab now, instead of me buying the two programs, you have convinced us that both programs can do the same job with the same results.
Okay.
Which one should I buy in terms of cost implication?
Regarding your question, some of these programs are sent directly by the manufacturer, that is, those people that develop the programs. For example, the Ogdo software that I make use of, I got it from Ernest Oze, who is a medical physicist in Canada. So it depends on the accessibility. However, PCSMC software required a lot of way in installing the software for use in a lab, basically in medical, in clinical use. Do you understand what I'm saying? So because of the availability of the Ogdos, I will prefer that you make use of Ogdo software as well.
Thank you very much.
Yes,
And
sir.
also, in your presentation,
Yes, sir.
you compare the result of the two softwares.
Okay.
But how do we measure the original experimental results? I don't
Yes,
get me.
just as I told you, there is reason for making use of these programs. And the reason is because you cannot directly measure the organ dose during a patient examination. One method, which is also a direct method of doing that, is to have a phantom. By the time you model the phantom for that particular patient, and the difficulty in doing that is because for that particular patient, you have to mold the phantom, which must be of the same size with the patient that is undergoing the clinical X-ray examination.
It's difficult.
And for you to do that, it's going to take a lot of time. There is difficulty in
Difficult.
doing that. And so because of that, that is why these softwares are being generated for use in clinical examinations.
Okay, thank you. I hope you, maybe from Africa, we could develop similar software that does the same job in later future.
Yeah, I'm currently working with the man that sent this the Hogdos program to me, of which one of the method to do that, at least to come up with the program, is the use of EGNCR Monte Carlo expression, which I am about to learn. And I believe strongly that once I am through with the learning, I can generate different programs for different examinations.
Thank you.
Thank you so much for your questions and the answer. Now we have Dr. Olubi, who have a question as well. So please be quick. Yes, we still have 4 minutes. That is fine. You can ask your question.
All right. Thank you very much. I was going to ask the question of how are there no written mathematical relationships that can help calculate those doses, the effective dose and the organ equivalent dose? But he has given answers to that. I however think that for Mr. Laushun, I would like to ask, do you have an idea of some of those parameters that go into the formulation of the mathematical relationships that exist in those programs, in the programs? Because
I can hear you.
I am saying, do you have an idea of some of the parameters that go into that program, go into those programs? For example, you mentioned the size of the subject, and are there other things like that has to do with skin material? For all of us is the same, I want to believe, but I think the knowledge of all those can aid your learning of even your similar. We need to know what goes into the program that can make, for example, somebody like me different
Sorry.
Okay, now I can hear you. I'm trying to show you the parameters that I have here.
So,
Hello, can you hear me? Hello?
Hello.
Yeah, the parameters that each programs required, you have the age, you have the gender, you have the KVP, you have the MAS, you have the FSD, and the filtration for that particular exam. Those are what I have shown on this particular page for each of the examination that I consider.
Okay.
We take the measurement from the patient information, we give you the age, the gender, then the FSD is the focus to source distance, that is the distance between the source and where the patient is that taken. The KVP and the MAS, they are the machine parameters that are used for this examination and the filtration as well. So those are the value, the parameters that are inputted into the computer programs, which give you the organ equivalent dose, the effective dose, and some other things as well, which the programs can be used to generate.
Okay. I am looking at it from this perspective of comparing both programs.
Okay.
There should be a standard. There should be a standard against which we are comparing.
Hello.
Hello. I think we lost him. So
okay.
Maybe
comparing both.
Uh,
All right, I'm okay.
Hello.
Hello, I'm okay. I'm okay with Mr. Olaoshu. I'm okay.
Yeah, please let me zip something in, please, Mr. Olaoshu. Do you consider the computation time for both programs?
Hello, sir.
Do you consider the computational period or time for both programs?
Yes. On the computational time, I think all those is more faster than PCSMC.
What percentage difference?
Hello, sir.
What was percentage difference?
I did not actually find out that with this study on the time.
Okay. So I think the discussion is getting very interesting. So I think the topic is interesting to everyone of most of the people. So maybe because of time, we continue with the next one, and then at the coffee break that will happen just after the next presenter, then we can keep on discussing on the topic, right?
Thank you, Mr. Dr. Dan.
So please, can we just switch to Mr. Thank you, Obayomi, for your presentation again.
All right. Sir.
And can we switch on to Adewale, if he's online, Mr. Adewale? I don't know whether I'm pronouncing it well, but do you think he's around? Because I didn't see him in the list. Adewale Olalekan. He's not here, I think. Okay. Oh my God. So we have two people missing then. Okay. So I think he's not here. So we just what we'll do is maybe we go for our break now, and then for 10 minutes, and then we start just after at 20. What do you think about that? Our coffee break, 10 minutes. Is that fine for you all?
It's fine for me here.
Okay, so please let's go for the coffee break, and then we come just here at 20
That's how many
past.
minutes, sir?
So 10 minutes.
10 minutes. All right. Thank you.
Okay. Coffee break without coffee.
Yeah, without coffee. But you can just take some water and drink. That will
That's
make it.
virtual coffee. It's virtual, actually.
So by the way, if you still want to discuss about the presentation of PCX, MC, and all those, you can just continue the discussion because it's still open.
There is one hand raised there. From,
okay, Onia, Ebenezer. Onia Ebenezer, I'll give you the floor now. Just a minute. Okay, you can just switch on your mic and speak.
Hello, can you hear me?
Yes.
Oh, thank you very much. So it is just an observation that I think maybe it will help in the course of presentations. I believe we should have an e-copy of the book of abstract.
Yeah.
Made available for all the participants. So it will help us to follow better each of the presentations.
Okay.
I don't know if that is still possible.
Yeah, I think, I don't know, we are planning to make an abstract book, but I'm not sure it is planned for just during the conference, but just after the conference. I don't know, Dambe or Dr. Latif, do you have something to say about that? Sorry?
I'm sorry. The point is that the person who was in charge of it was a little busy. And so we decided to give it at the end with the presentations, PowerPoint, PDFs. So you will get it with the presentations, and then you can, I don't know, reread the presentation at home quietly.
Yeah, I think his remark was very important, because if we have the abstract book, people can actually know what people are going to discuss before. Yes, and we didn't realize people don't have access to the abstract of people. So yeah, so you are right. We'll try Dr. Ebenezer Onia to correct that for next time.
Okay, thank you.
Yeah,
welcome.
last year when we I said last year, 2 years ago, when we did it in live, then we could do that. But now, since it's virtual and it's our first time, so we are managing for now, and from this one we'll learn new things and continue on the next edition. And I don't know where it will happen next year or in 2 years now. So who knows? Maybe you'll be part of the organizer, and then your idea will be actually taken properly into account.
Okay, no problem. You are doing very well. So
Yeah, we are managing. Thank you so much. Okay. Abstract. So maybe we check Eric Ziki. Eric Ziki from Ivory Coast. Are you around? Let me check those who are presenting next. They are already in. Eric Ziki slide. Okay. Let's hope he will connect now. Okay. And Ridwan Afolabi.
He was around.
Where are all these people?
Yeah.
Ridwan Adeyemi Olorantoba.
I think
Are they going to?
Adeyemi, I think he sent an email. He was complaining about connectivity.
He sent an email.
Yeah, I hope he'll get sorted.
He will be able to
soon.
connect.
No, I just hope.
Yeah, okay. Let's hope together. And
okay, I think
Emmanuel Faboro.
Ademi is back.
Okay, Ademi is back. Ridwan Afolabi is back.
Okay, Eric Ziki, we should. Okay. And then we have other people. Oh, we have 2 coffee breaks today. You guys should provide coffee then. So me,
Future
hello,
coffee.
Azote.
Hello.
She's on now.
Yeah.
Okay.
Hello.
Internet is getting so hard. We can't hear you properly, but I guess you are just connecting. Okay, I saw Ridwan as well in now. So it's Ridwan, you are connected to 2 devices. Hello.
Hello.
Mr. Ridwan Afolabi, I think you are connected to 2 devices.
No, just only one device.
Yeah, are you connected to 2 devices? It
No,
seems
just one device.
yeah.
Can we let Mr. Abayomi make a presentation and then?
Yes.
Time is going on.
Yeah, we are starting in 3 minutes. We are at the break now.
Or we can make just 5 minutes of break, so not because we are a little late.
Since we told people 10 minutes, maybe, yes, we are already preparing now, so it's fine. So who is Ridwan? Will you start now? Can you prepare your presentation and start sharing your screen, please?
It's Abayomi who will start. She is back.
Hello.
I think, oh no, Afolabi.
Hello.
Abayomi. No, Abayomi was already there. He already did his presentation. It's Adewala who was not here.
Okay.
Abayomi, yeah, he already did his presentation.
Okay, it's Adewala. Okay. So Adewala who was not there.
Adewala was not here.
Okay.
So now, since we don't know, I can't see Eric Ziki from Ivory Coast. So maybe.
Yeah, I think Mr. Ridwan Afolabi can start sharing his screen.
Yes,
So
Afolabi Ridwan, please start sharing your screen. Is that your screen shared now? Or I think this one is for Abayomi,
yeah,
right?
it's still
yes.
It's still Abayomi.
Can you
should
stop sharing? Okay, good. Ridwan, you can just start sharing your screen now. And
All right.
are you hearing us, Ridwan?
Yes.
Okay, good. You can, yeah, we can see your screen.
Turn your phone in landscape. Turn your phone on landscape.
You are using your phone.
You are using your phone, I think. Turn it landscape.
Landscape. Okay, sir.
Yeah. Great.
I hope it is okay like this, sir.
Is it okay?
Yeah, the screen rotation should be allowed. Yes, that's good. Please stop zooming. Just make it once. If you are zooming, we cannot actually follow. Put it the
Alright.
correct. Yeah, that's fine. So please just fix it somewhere, and then we can just start now. The presentation, you have the floor, and you have the questions. You have the floor.
Okay. Good afternoon, everyone.
Hi.
I am presenting the effect of exposure to radiation from telecommunication masts on the liver of whisperers. Hello, sir. Hello, sir.
Yeah, we can hear you. Go on.
All right, sir. I'm Afolabi Ridwan from Obafemi Awolowo University, Nigeria. Talking about the electromagnetic radiation, it refers to the way of the electromagnetic field, which are radiating through space, carrying electromagnetic radiation energy. This electromagnetic radiation are absorbed in the body and produce heat, but the normal body thermoregulatory process, they are the one that carry this heat away. All the established effects of electromagnetic radiation exposure are related to gamma effect. Moving to the animal preparation and exposure. In the experiment, we use a total number of 30 whisper rats, both male and female, of age 6, which weighed 150 grams. The animal was separated into 6 different groups. We have 3 groups which contain the male, and then 3 groups for the female rat. So we have group A, group B, and group C, which contain 5 male rats each, and D, E, and F, which also contain 5 rats each. Group A and D serve as the control rats, which are placed in the control room, and the other 4 groups, which are Group B, Group C, Group E, and Group F, are placed 5 meters away from the telecommunication mast. The animals were kept in a photo period of 12 hours of darkness and 12 hours of light, with easy access to food and water. The animals were put in a standard animal facility, and wood shavings were used as the bedding. So for the measurement of the radiation, the site was done to avoid background radiation of the environment, to know maybe there are other sources which are emitting radiation in which we do not know. So with the aid of the survey meter, the probability of interference from other radiation was determined. Besides, the site with which the high altitude were avoided since oxygen level is inversely related to the height. The non-ionizing radiation from the telecommunication mast was measured with an electrosmog meter, which can test the electric field strength and also the power density of the radiation. After 120 days, the rats were sacrificed under anesthesia, and their blood was drawn into blame bottles to determine the level of alanine aminotransferase and aspartate transaminase. The liver tissues were collected and homogenized into hydrochloric acid buffer for histological assessment. After the blood collection, they dissected from the abdominal region and fixed in a former saline for 72 hours and sliced into a thickness of 2.0
1 millimeter. The tissue was hydrated with alcohol. So later it was further treated with paraffin wax and casted into block. Section of tissue were then cut into microtome of 5 micrometer. So this tissue was stained with hematoxylinogen and examined under a light microscope. So moving to the result and discussion, the radiation index measurement, the background radiation of the area, which was monitored with a thermometer to check if there is external production of radiation source around the telecommunication mass, reached 9 to 8 nanosieverts per hour. This was monitored just to see if there is any interference of any other radiation other than the radiation from the telecommunication mass. For the aspartate aminotransferase, which is the AST, the graph below is showing the variation in the aspartate aminotransferase level. The graph was showing that the liver, there is no. Okay.
Yes. Sorry. Do you have another session open like YouTube live or something?
No, sir.
Because we're having echo.
No, I'm in a silent place.
Okay, you can go on.
So the graph below is showing the variation in AST level of the rat. There was significant decrease in the level of the aspartate aminotransferase level.
Excuse me, Adeyemi and Abayomi, can you stop your video? And also, Ridwan, please don't switch on your video. You can go ahead, please.
In the graph showing the variation in the AST level, there was significant decrease in the level of aspartate aminotransferase for the exposed rat when compared with the control rat. The low level of AST in the liver shows that the liver is healthy. For the alkaline phosphate, the graph below showing the variation level of the alkaline phosphate. There is an increase in the ALP enzyme level of the exposed rat. Suggests that it depends on the exposure period. This ALP, which is the alkaline phosphate, it is an enzyme which are found mainly in the bile duct of the liver. Increase in this ALP and another liver enzyme can cause obstructive or cholestatic liver disease, where the bile is not properly transported from the liver because of the obstructive of the bile duct. It can lead to liver disease. So when the liver is damaged, the ALP, which is the alkaline phosphate, may leak into the bloodstream. The high level of ALP indicates liver disease. Histological test. This histology is the study of the microanatomy of the cell tissue and organs seen through a microscope. It examines the correlation between structures and function. The figure below shows the result obtained from the histological test, which shows that there were no remarkable significant changes in the arrangement of the liver cells
in the control and animal exposed to radiation from the telecommunication mast. The photomicrograph here for the control male and the control female shows that the hepatocyte, which was labeled H, and the right achromatic nuclei with prominent nuclei, which was labeled L, they are intact. Then the lineable hepatic veins called the central vein, which is labeled CV, are also intact. So this shows that the arrangement of the liver cells are in control for both the control group and the animal exposed to radiation from the telecommunication mast. The discussion now. Our findings demonstrate that the continuous exposure of electromagnetic radiation emitted by the telecommunication mast to the Wistar rat alters enzyme activity in the liver. This liver of a thing is an important metabolic tissue and main organ of detoxification. The reason for selection of liver was its sensitivity to waste products. And one of the most important features of these pathological changes of liver cells is the change of the level of liver alkaline phosphate and aspartate aminotransferase enzyme in zero. During the cell injury, because of higher permeability of the hepatocyte membrane, this enzyme they penetrate to sinusoid and then enter. And then enter because of higher permeability of hepatocyte membrane, this enzyme penetrates to sinusoid and then enter into the peripheral blood, and an increase in level of such enzyme is observed. High level of alkaline phosphate can indicate liver disease or bone disorder. High level of alkaline phosphate can also indicate disease like cirrhosis, hepatitis, blockage in the bile duct. So if the aspartate aminotransferase and the alanine aminotransferase in the liver are normal and the alkaline phosphate level are high, it means that the problem is not in the liver. Instead, it indicates bone disorder, such as Paget's disease of the bone, a condition that causes the bone to become abnormally large, weak, and prone to some fractures. In conclusion, it can be concluded that exposure to electromagnetic radiation emitted from telecommunication masts can cause tissue damage. Also, the alteration of the subbiological of hepatic tissue can be caused by exposure to electromagnetic radiation. Based on this animal model study, such effects are also expected to humans. Therefore, it is suggested that long-term exposure to telecommunication masts or installing masts close to residential buildings should be avoided. Thank you, sir. This is all I have, sir.
Okay, thank you so much, Ridwan, for this presentation. So you also finish in time. So we have now 6 minutes for questions. So you can just raise your hand for those that don't have the panelist membership. So please go ahead and ask your question. Just raise your hand in case you have a question. Yeah, you can go ahead.
Can I? I have a question for you. So first of all, well done for the very good job. And I am actually curious about how you how I'm not sure you'll be doing it, but how people actually transfer this to human. Is there any clinical study or like, and how the methodology, how the experiment will be designed? Because I guess they won't use like human liver and do some histology tests on them. I'm not sure. Or is there anything about cadaver or something like that?
Huh?
So how is the experiment will be translated into human being? Is there any current clinical study that are been doing?
The reason why the Wister rat was used was that the Wister rat has the same metabolic structure and system with the human being. That's why the Wister rat was chosen, because normal human being cannot be used for experiments like this. So that's why we choose to use the Wister rat, because they have the same metabolic system with the human being.
Okay. Okay. So now my question is, how do you try this like in human being? Is there any other kind of experiment that you guys can design instead of using like the same protocol, the same methodology? Is there anything that is non-invasive that you can use for human being? So first, is it possible first?
Hello, Ridwan. Are you still on?
Yes, I'm online.
Okay. So did you understand his question or?
Yes, I understand, sir. So he was trying to say that is there
I think
any experiment that we can carry out on human beings to know the effect?
yes, the question is about the transferability of your methodology to human being, because the end or the main goal, the end goal of your study is to be able to understand or to make it on human being. Like that's how people are exposed to telecommunication radiations, right? So how do we transfer this?
Hello,
I
sir.
think
Hello.
If we must transfer this, that means since both the rats and human being
Okay.
has the same, then we have to
Okay.
make sure that human beings are not exposed to too much radiation from the telecommunication mast by building residential houses not close to telecommunication mast.
hello,
Yeah.
hello,
Okay.
hello, Dr.
Okay.
Dambi.
Hello, you can go ahead.
Yeah, I
Hello.
think, I'm sorry, I think
Hello.
the essence of this research is to show
Yeah.
that if this radiation can affect the liver of this animal in a particular way, it should affect the liver of human being in the same manner. Therefore, the inference can be drawn from the results of this animal. I think that is the essence of the research.
Yeah.
Yeah, so it means in some sense that the conclusion he makes for his study is directly transferable to human being.
Yeah, directly.
There is no correction to make or any kind of adaptability, nothing.
No, because the liver of human being is similar to the liver of this animal.
Mm-hmm.
If the exposure can affect this animal in this manner, definitely it can affect human being in the same manner. Then human beings should be careful while building their residential apartment closer to the mast.
Okay. I have a very fast and quick question to him.
Hello?
What is in Africa, for instance, or let's take Nigeria, do we think the rate of exposure now for the radiation from telecommunication is too high in our countries? Is there any data in that sense?
If I can come in, Mr. Ridwan, I think
Yeah.
I'm sorry. I may not have empirical.
Yeah, it's okay.
I may not have empirical data, but I've seen an event in a city in a state in Nigeria. The state is called Osun State.
Yeah.
There's a city there. The name of the city is Ede. The father of my friend built house, and they put mask closer to their building. I'm telling you, within a year, all the residents of that building, they developed some diseases, and the father died of it.
Okay.
The father died of it. The wife died of it.
Oh my God.
Until all of them vacated the building.
Okay,
I'm quite
so
aware
it
of
seems,
that.
yeah.
But we did not investigate further. What is the percentage of radiation? How did it happen? We did not go there because I was not in Nigeria then, actually. But it happens.
Let's see. I see. Then is a clear evidence that from at least at some point it happened in Nigeria.
Yeah.
So I think yes, it's something that could be very dangerous then. Yeah, because in some countries, the reason why I'm asking the question is that in some countries there are regulations. For instance, for telecommunication, you need to emit in your radiation should not exceed some kind of exposure for the population in some sense.
Yeah.
But I don't know whether we have these in Africa.
We don't have that in my country. I don't know that countries actually.
Okay, so thank you so much for your contribution.
Yes, sir.
Yeah, so please, can we go to the next presenter? Mr. Dr. Eric Ziki is still not around. I can't see him. So Ademi, are you in? Ademi, seems I saw him just.
Yeah, he is.
Yeah, Ademi Calvin.
Just have to unmute.
Yeah, but then is he Ademi Calvin? Because I'm seeing Ademi Calvin here. So let me try to unmute Calvin and see.
No, we have Olurutumba Adeyemi here in the panelist group.
Oh, in the panelists, in the part.
Yeah.
Okay.
Yeah.
Oluruba. Then he needs just to unmute his mic. Adeyemi, could you just unmute your mic because you are allowed to speak now. Hello. Hello. Okay, Emmanuel Faboro also is not around, so we'll just pass to another person before we. Dr. Somi Alo Azote, can you just take the lead? Dr. Azote Somi Alo, are you connected? She's connected, but where are they? Or they cannot unmute the mic or what? Hello. What's the life? This is the last person before the next coffee break, and the three people. Ademi is there but cannot speak. Azote Somi, hello.
Hello.
And hello, who is there?
Onia. Hello.
So hello. Azote, could you wait a minute, please? Who is that Ademi? Because I can't see who's speaking.
No, it's Mr. Ebenezer Onia in the attendee group.
No, I'm just suggesting that maybe you ask them to raise up their hand.
Yep.
Hello.
Okay, yeah.
Yeah, if you ask them to raise up their hand,
Yeah, is okay. Could you raise your hand, Dr. or Mr. Adeyemi Oloru Toba? I can see him from the panelist, but he is not unmuting his phone. Emmanuel Faboro, if you are online, please raise your hand. So we'll continue since Azote is here. She can start, and then we'll just wait for the other people.
Before we go
Dr. Azote, can you just take the lead?
All right.
Before Dr. Azote can start, Dr. Beltaco, can you please go to the attendee group and add Mr. Adeyemi Kelvin in the panelist group? Maybe it's the same person.
Mr. Ademi just wrote.
Mr. Adeyemi.
He just sent a chat message.
Adeyemi Kelvin. Okay.
There's someone raising their hands.
He's saying he can't share his slides.
Oh, okay.
Yeah, because he's not in the panel list.
Okay, so if Dr. Azote is
Adeyemi,
ready, she can start.
Yeah. Okay, Azote, you can share your screen, start, and then after Adeyemi will present. Okay.
All right.
Okay. Thank you.
Welcome. Can you see my screen?
Yes, we can see. Please go to the presentation mode.
All right. Thank you for this opportunity to present some of the results of that we have done for my PhD work. So,
Do you, Azote?
Yes. Do you hear me?
Yes, we hear you. Could you use the presentation mode?
Oh, sorry. Okay.
Great.
Is that fine?
Yeah, it's fine now. Please go ahead.
Okay. Yes. Okay, I was saying the topic I will present here is about actin network, branching actin network inside cells. So I will first introduce and then motivate. After that, I will present the model and some first result, then the extension of the model, and then present some of result, and then conclude. So for this work, we are basically interested in what are the elements that contribute to the cell mechanics. Basically, the main element is the cytoskeleton, and we are mainly interested in actin network, which is one element of cell cytoskeleton. So basically eukaryotic cells. So we will develop this point and then introduce some of model known as polymer model that are used for actin filament, and then extend it to study branching actin network inside confining region. So as I was saying, here we have the drawing of animal cell and the plant cell. They have a common element called cytoskeleton here. I took the image from Wikipedia to it represents here an image, the imaging that have been done, observed via experiment. And then here a cartoon of this cytoskeleton. And the cytoskeleton of eukaryotic cell are mainly composed with microtubules, actin filament, and intermediate filament. And as I said before, we are mainly interested in branching actin network. Why? Because branching actin network are the most contributing element of the component that element that contribute most to the cell mechanics. So here is an example that has been, here is one of result by Efimova and all, who published in 2018, where they show that branch actin network are allow cell to keep the adhesion within the tissue. So what favor what gives the strength to actin network is that actin networks are the most abundant.
Hello?
Hello? Actin network.
Yeah. There is a nose around.
Yeah, sorry, we have okay.
Can I continue?
Yes, you can continue.
I think so.
Okay. Actin network are the most abundant inside cells, and here is I show an image and I try to represent by the cartoon. And the one that are most abundant are branching actin network, and they are mostly, they reside at the edge of the cell. And what they do is they push against the cell membrane. As they grow, they branch via a protein known as up to 3 protein complex, and then they branch against cell membrane at 70 degrees. So experiments have shown that within the tissue, the stability of cell depends mainly on the elasticity of branching actin network. The elasticity of branching actin network in turn depend on the topology and how they orient inside the cell and how they are spatially organized. However, when these in turn is controlled by the effect that the confining region, like the effect that the cell membrane introduce. And if the organization inside the cell fail, then it leads sometimes to cell fates or cellular diseases such as cancer. So this motivates this study, and we would like to know what are the parameters that influence or that affect the spatial organization and orientation of actin network inside the cell, and what is the implications of these conforming structural behavior to the elastic to the mechanic of the cell. So basically, why, as I was saying, the cell actin network are confined by the cell membrane because they are similar. Actin filament have a certain length that is similar to the cell size. So this causes the confinement effect. As the drawing here that I show, if the filament, a linear filament is an unconfined state, then it looks longer, but then it has to stay within a small size, which is cell. So there are obviously some effects that affect the rearrangement, the orientation within the cell. So there are models known as polymer model that use tools from statistical physics to study the structure or that can be used to study the structural properties and mechanics of these network. So we
You have 5 minutes, please.
5 minutes.
Yes.
Okay. So basically, okay, these are the model that exist, one of the model that exist for linear chain. But then, okay, here, this model is known like as one like chain model. And then we cannot use this because it has constraint, inextensibility constraint. So we use another model known as a grand canonical monomer ensemble model, which enable us to define a grand canonical partition function here given by equation 2. And then knowing the grand canonical partition function, we can then, this is for linear chain. This is done before, and we base our theory on this, and we develop a model for branching actin network. So from here, we define a partition function, which we represent here diagrammatically, and we can write it into integral equations. Then we solve it. We have also defined, using this equation, we cannot calculate the density profile of, okay, we use this equation, then we have to define our region for the confinement, and it is given by these equations here. Next, what we do is to calculate the density profiles of and other parameters that allow us to investigate the structure and conformation of actin network. I'm going straight to the numerical result. Here, what the parameters that we basically based on our study here are the chemical potential of actin monomer, the chemical potential, which is Z0, and the chemical potential of up to 3 protein complex. So as we vary this, we obtain various type of network, short network made up of short filament. You can see it here, and this is given by the this is known by the other parameter. So as we increase the values of monomer inside this, the confining region, which is spherical cell here, we can see how the other parameter and the density profile change. So we have obtained, with this, we obtained a phase diagram, which enable us to classify different type of actin network. And we reach the case where we obtain a dense branching actin network. And this is seen also in experiment where we see actin network growing perpendicular to the confining region and leading to the formation of lamellipodium. So the second result is that we look at the stabilities of the cell and we took simple geometry of cells to see if can the network change the volume of the cell. We see that the actin the cell within a tissue is stable. It cannot, the volume is conserved throughout any mechanical force given by actin network. So this we knew this by computing the free energy of the system, by computing forces, by computing also the Young modulus of the system. So we also look and see if we share the cell, can the cell within the tissue stay stable? Then we saw that it becomes unstable when we go beyond an angle of p/4 and or less than p/6. So the stability only is obtained between an angle p/6 and p/4. So with this, I would like to conclude. So here we formulated a model for branching actin network, which enable, and this calculation is at equilibrium thermodynamic. This enable us to investigate the structural and the conformational property of actin network under confinement. And then we look at the implication to the mechanics of the cell within the tissue. This result can have been tested by other group experimentally. And also this finding will help in understanding, like it will help, is important in the diagnosis of cells, sick cell, like in the field of cancer study. Also, it will help also in the conception of artificial cell. With this, I would like to thank our founders and then thank you all for your attention.
Thank you so much, Dr. Azote Somialo, for this presentation. And I think we will have very sharp questions for 4 minutes. So questions are welcome now. Just raise your hand if you want to talk, and then we give you the floor. So before the questions, so I have a questions like, how does you said these results have been confirmed experimentally. How does the experimental result compare to your numerical simulations?
I said it has been testing, so it's
Testing.
not yet. Yeah, they are still testing.
They are still testing.
Yeah, a PhD student working on it.
Okay, I see. Then for the the diagrammatic representation of 1D linear chain, what I wanted to know, is there any connection of your diagrammatic representation and Feynman diagrams?
No. Are you talking about?
No.
Oh, are you talking about?
Feynman diagrams, but
Yeah,
I think it's
I think it's the same thinking, you know.
yeah, because there are specific rules to make these Feynman diagrams and so on.
Not
So I
really.
wanted to.
Yeah, but this is just an integral representation to more understand the mechanism of the formation of the chain. So you can see it like is something similar to Feynman diagram, but not really.
Okay. So yeah, do we have any other question?
Yes.
Am I the only one speaking or someone else is listening to us?
Hello. Can you hear me?
Aye, okay, good. Then
Yeah.
at least
We
we
can
are
hear
not alone.
Thank you so much, Dr. Azote, for your very good presentation and so many results. So my first question is, you actually did some, is it mechanical test where you use I think you use load and share.
Okay, let me see.
I think it's some no.
Here.
Yeah, exactly.
Okay.
So are you saying that the compressibility of cell is not that pronounced, like is it
Yeah.
something you can say?
Yeah. For example, within the tissue, let's say we consider. Do you see my mouse?
Yeah.
Okay. We have a
You
system
can
where
also
we
can
check.
also draw with Zoom.
Come again, please.
You can also kind of draw or edit on Zoom.
Okay. Yeah.
Do you know
That
that?
is true.
Yeah,
Yes.
but it's fine. It's fine. We can see.
Okay. Okay. So we what we tested is to see with our model if it happened that one cell the active network is growing against other. What will happen is the system is the model stable. So that is why we checked and we saw that okay, we can confirm that the cell within the tissue as the actin, even if it grow more, obviously the actin network will not go at the same speed inside all cell within the tissue. So that is what we tried to check if the volume of the cell is conserved or not.
Last small question. Do you have any idea of other proteins that will be targeted apart from up to 3?
Yes, we know there are other proteins, but we have not really incorporated it here. You know, modeling branching actin network is not that obvious. So we only consider one protein to see what will happen.
Okay, thank you.
Yeah, you're welcome.
Thank you. There's a question in the attendee.
Okay.
Ludovic Akona.
Yeah, Ludovic Akona, you can just go ahead.
Okay. Okay, thank you very much, Dr. Azote.
You're welcome.
I've learned a lot from your presentation, and I have a question for you.
Okay.
I think in the introduction, you said that disorder in actin network can lead to cancer. So what I want to know is the information you extract from your model, can they help us prevent cancer or maybe heal from cancer? Okay, this is my question.
Okay, it's not directly linked, to cancer, as we know it, but knowing the structure of how component inside the cells behave will contribute to design. When a drug are designed, knowing how each element inside the cell behave will help in design the correct drug. Or if, like, let's say, okay, with this we can know that, okay, if we extend our study, we can say, okay, when we take, if we do experiment, we will take normal cell, do this experiment, take 6 cell, do this experiment, and then we compare. This also will help in doing the diagnosis. We will see, okay, what are the structure of active network in a 6 cell, and what are the structure of active network in a normal cell.
Okay.
Okay.
Okay, thank you very much.
You're welcome.
Okay.
So Dr. Isiaka wanted to ask a very quick question because normally we are almost done. So he will just ask his question through my phone.
Okay.
Thank you for your presentation.
You're welcome.
What kind of hypotheses do you use to elaborate your density matrix or operator, density operator?
I'm not sure if I understand your question.
Because in your
kind?
presentation, you are presenting a kind of density operator. See equation 16, for example. Is it the
Okay.
density operator or how kind of density it is?
What kind of density?
Yes.
Yeah, the density here is a kind of probability. They have is an average probability of finding monomers chain inside a system. I'm not sure if I understand very well your question.
Yes, it seems like the density operator in quantum mechanics. Because with the density operator, we can also deduce the probability of a measurement of a system.
Yeah, that is the kind of same theory, yeah.
Yes, and how do you calculate the entropy in of your system?
The entropy.
Yes, is it possible to calculate here?
Yeah, okay. If we can calculate the entropy of the system, if you see here, in order to analyze or test our model,
yes,
to understand it to the tissue, we have calculated the free energy. That is the plot for the free energy here. I don't know if you see it.
Okay,
so,
okay.
Yeah.
And with this entropy, is it possible to have some idea of the state of cancer of a cell in medicine, for example?
Yeah, like not really yet, because it's not really an advanced model here, because we are not incorporating many elements in our system. Already this is very complex, and maybe in future we are thinking to adding more component that are inside the cell.
Okay, thank you.
You're welcome.
Okay, thank you so much, Dr. Azote, and I'm sorry we went beyond time for 5 minutes.
Sorry.
And it's just because you are the first lady speaking in this today's section. I don't know whether we had a lady yesterday, but
We had
thank
one
you for.
before.
We already had a lady, right?
Yep.
Okay.
Okay. All right. Thank you.
Thank you.
I will now stop sharing.
Okay. Thank you so much. So, do we have Ademi is now on?
Yes,
Please,
sir.
could you stop sharing? Okay, thank you. Now, do you have the right to share the screen, I think?
Yes.
Okay, please, you can just start sharing, and then we look at your presentation on the effect of exposure of telecommunication as read one, right?
Yes.
Okay, so just go ahead. You have the floor now.
Are you seeing me, sir?
Not yet. Maybe, have you shared your screen?
No.
Okay, please start sharing now.
Okay. Okay. Are you seeing it, sir?
I think the process.
Yes, we can see your screen now. So
okay.
Go to presentation mode.
Okay.
And then
Can you see it?
Presentation mode. Yes, yes.
Okay.
That's fine. Yeah. Thank you.
All right, Amademi Olontoba. So I want to present on the effect of exposure to radiation from the telecommunication mast on the kidney of Wister rats. So, firstly, I want to introduce this thing as radiation is the emission of energy in the form of wave or particle through space. And then we know that there are new development in telecommunication due to the movement from 2G to 3G to 4G and 5G, which is detrimental to our health. And then we have so many mass that still will come. For example, in Nigeria, we are still using like 204 million by NCC, which could still be much more in 2025. And then now, let's look at the research methodology. We bought 30 rats, which are weighed 100 to 120 grams at Obafemi Awolowo. So these rats were grouped into male and female, but we have two groups which are kept at the control room, and we have other groups which are kept at the experimental room. So now, the measurement of the radiation.
Friday,
we need to measure what we call the background radiation of the area that we want to do the experiment by using survey meter. So using the survey meter actually could note that there are no external or other forces that are being measured. So after measuring with the survey meter, we now place the rat at the control and equally the exposed area. So these are the calculations for the exposure, that is the potential, the potential and the experimental, the power density and the E of the something. So this is the mass and the electrosmog meter that we use to do the electric field and the other one. So now we move to plasma creatinine. To collect the blood sample in the rat which have been killed or which have been sacrificed, we need to collect their blood into a lithium heparin bottles, which are now taken to the lab and have been tested using Redox laboratory
limited, which we have tested the creatinine and the urea with it. So measurement of the weight of the body weight now, we use weighing balance, which are being done by Camry, Zhongshan, Chuandong in China. So now the biological assay, centrifuge of the blood sample, this is how we do it. The blood sample was placed in the centrifuge that have a speed of 200 rounds per minute within 10 minutes. And the measurement of the kidney, which are being used, the kidney are very small. So we use a Camry weighing balance, which are digital. So homogenization of the kidney samples. The homogenate are being done in the lab and the biochemistry lab, which are being grinded and which are being using a blender to blend it, and then which we now tested the tissue, and we now tested the antibiotics, which are the catalase, the SOD, and the GSH. So we now use the statistical analysis. We calculate the statistical analysis by using what we call a graph pad, which we use the one-way ANOVA analysis, and which we use Microsoft Excel 2013 too. So now the result from the background radiation, experimental area was monitored with a survey meter to check if there is an external production of radiation source around the telecommunication map. That's what I've said. Then measuring the RF radiation with the electron smoke meter, I measured the power density and the electric field strength from the mast in two directions. Firstly, very close to the mast, and at the same time, very far away from the mast, which we kept our control animals. So now we look at this little diagram. Is the mass set from domicile building from 2001 to January 2014. They said that the regulation should be 5 meters setback, and from 2014 they said the regulation should be 10 meters setback. That is Nigerian, National Communication Commission and the National Environmental Standard and Regulation Enforcement Agency. So now we move to the readings which I got from the experiment. I now got the power density that is close to the mast and power density far away from the mast. I got the electric field and the electric field far away from the mast and close to the mast. So from the study, power density of the mast was found to be between 15.8 to 85.9 milliwatt per meter square. And the other one is 0.011 to 948 microwatt per meter square. So, and the electric field is now 2.4 to 5.6 volt per meter, and 396 to 951.2 millivolt per meter at the exposure location and the far away from the location respectively. So I don't know if you got this very well, but something I don't know. So we now see that early stage of the food consumption now. We test the food consumption of the animals. That is how they are feeding, and are they feeding equally or differently. We can see that at the early stage, the animals and the exposure, they don't have a significant difference. And at the latter stage, there's a significant difference. The control were able to feed very well, and but at the exposed, they were reduced because there's a significant difference. If you look at it, you see a star here, which I used to signify a significant difference. So, and we use the N is equal to 7, that is 7 animals. So After that, we now test their body weight of the rat. We see that at the early stage, they are almost the same as their weight. And at the middle stage, there's a significant difference. And at the later stage, there are more significant difference. Okay? So I now move to the plasma creatinine and the plasma urea. From the result, I got an significant exposure from the plasma creatinine and the plasma urea. There's high values being obtained. So this is the T and this is the P is got less than 0.05. And at the second part, we test their urine from creatinine and the urea. So we can see that it's only the urea that has a significant value. So if we now move to the SOD, GSH, and catalyst, which are now the major thing that we want to see. We now see that the GSH and the SOD are significantly different, while the other one has no significant difference. So this is the creatinine clearance of the animals, and this is the histopathological something. So this histopathological, we now see that there's a wide urine relative to the control group, which is this, and relative to this. So this is the control, this is the control, and this is the exposed, and this is the exposed. So the conclusion now, due to the unknown and known effects of radiation from telecommunication mass, this is very necessary to ensure that place of residence are not situated near the mass, since there are effects of living organisms, including human, might go on for a long time unnoticed. So, thank you. Thank you, sir.
Okay, thank you so much, Ademi, for your presentation. And I guess this presentation will raise also questions like in the case of Ridwan, but please, we still have, let's say, 6 to 7 minutes for questions. So feel free to ask questions now. Just raise your hand in case you have a question. Hello. Okay, you can go ahead, Abayomi. You can go, Abayomi-san. Oh no, Mr. Abayomi, please go ahead.
All right, sir. Hello, Mr. Atoba.
Yes,
Thanks
sir.
for that wonderful presentation.
Okay.
However, I noticed that there are certain conditions given according to the to what you've shown from your PowerPoint, from the presentation thus far, that there is a certain meter to which the building, that is the residential building or any other building that human being should be, and maybe 5 meter or 10 meter or thereabouts. However, I noticed that your own experimental rats were kept at a very nearby distance to the Mars, which I think is not up to 5 or 10 meters. Now, my question is, at what condition could human being be exposed to such radiation, knowing fully well that the condition has rightly been stated? And I know that before any mask can be erected, the NCC and the regulatory body will be there to measure the distance, the right distance to which that telecommunication mast is going to be erected. So at what condition do you think that human being can make human beings to expose to such radiations with that particular close distance? I don't know if you get my question.
Okay. what you are trying to say is that at what distance should
Going to be at that distance telecommunication mast, since the regulatory body has already given the distance from the mast and the residential area. Because if there is no condition for that, hello, sir.
Okay, firstly, okay, so should I continue?
Yeah.
Firstly,
There is a noise behind. I think it's Adeyemi Kelvin.
Okay. So, firstly, when we are talking about the regulations given by the NCC, we can see that not every telecommunication mast are followed the regulations. And me looking at this, even at 10 meters away, I think there's still some effect being detected from the animals at the mast. So the regulations now, you can see that even if you check the NCC representation at 2020, you might see that they might have increased the setback of the people building houses in the close to the mast. So, but one thing I just have to say is that it's very advisable not to build closer enough, up to 30 meters closer to the mast. That is just my own experience.
Okay, so thank you so much, Dr. Taureg Olabi. You can just go ahead.
Yeah.
Are you? Yeah.
Mr. Akinyemi,
Yes,
thank you for the beautiful presentation.
Yes.
You see, the situation in our country here in Nigeria is very pathetic.
Yes, sir.
You may decide not to build a house close to mast, but your neighbor, if the mast builders like MTN, Glo, if they come to your neighbor and they want to buy maybe half a plot, 100 million naira, the neighbor will sell the half a plot very close to you. You have no options. God save this country. My question is that during the experimental investigation,
Yes, sir.
put the rat there at a particular location, 10 meters away from the mast and 5 meters away from the mast. See, the rats were not covered. Were they covered with anything?
Yes, they were.
They were covered with what?
They were kept in a house, in a small house that we built for them.
Made of what?
Made of wood.
Wood. Good.
Yeah.
You see, can we generalize this research with the what is obtainable? Because human house were built with blocks, with roofing sheets. Are we saying that the radiations, the intensity of radiation will not get reduced due to the environment where a human being lives?
Okay.
As compared to where you kept these animals, these rats.
Okay, of course, we know that every house built should have a window, and anywhere that a radiation can penetrate, is like air. So anywhere it can penetrate, it can equally set an havoc to individual building houses to the mast, closer to the mast.
Also, do you consider the height of the mast? Because the height might differ. And the height, the mast, are they of the same height?
No.
You think you can make good comparison in that case when the mast at 5 meters away from the building is taller or shorter than the mast at 10 meters away from the building? Or do you think the propagation of wave from the top of the mast to the ground cannot be affected by the point of propagation?
Well, it can, sir.
It cannot, or it can?
It can.
It means that you did not put it into the study.
Yes.
Use the same height.
It's maybe due to the length of time, sir.
Yeah. And this research, where was it carried out? Exact location, Nigeria.
At Obafemi Awolowo University in the school.
Okay, you use this mask in the school.
Yes, yes.
I hope this kind of research could be published in this journal so that we can present it to NCC to adjust their regulations so that everybody lives peacefully in this country. Thank you.
Yes, we are planning on publishing it, sir.
Thank you.
Hello, can I talk?
Yeah. Yes. Is that Abayomi?
Yes, sir.
No, Adeyemi.
Let me see.
I'm Abayomi. I just want
okay,
to.
Adeyemi.
Yes, sir.
Hello, is Abayomi?
I'm hearing.
Okay, yes, go ahead, please.
Okay.
Yeah,
I just want to make an input to the previous person that made an input as well. You see, one thing I have observed with the location of the mass is that even apart from the building, like the laboratory and some other things that are close to the mass, we also used to have some people that sells to the students in the night. And so, location where the mass is, I think there are a lot of people that used to walk
could you
around
just
that
tell
place.
the people speaking around you to just
Hello?
yeah.
Hello, we are here with you.
Abayomi, please go ahead. I think there are noises just close to
I
Kelvin.
think it is very, very important for us to ensure that these things goes online so that the regulatory body will be able to look into it, because some of the effects of this radiation, they are not for the present time. A lot of them are they are agglomerated, and later on some of the side effects of these things are seen, because the radiation from this mass is a non-ionizing radiation, so the effects are not immediately being seen. So these are effects that are seen later years, maybe sometime like 20 years, maybe 30 years. Do you understand what I'm saying? So I think it is very, very important because more concentration has been done on ionizing radiation without looking into the effect of this non-ionizing radiation. So I think this should go on to a large extent so that people can observe what is actually going on. And another thing I'm seeing is that even apart from 4G telecommunication mass, which I think this research was based on, there are more generations now, like 5th generation. And because of that, the intensity from this mass is going to even be higher than what we are seeing from 4G telecommunication masts. So while there is advancement about telecommunications, I think it is as well important to look about the side effect of this telecommunication mast so that the adverse effects will not be spread across the continent or across the globe. Thank you very much.
Okay, thank you so much. Thank you so much, Adeyemi, for your contribution. And is Abayemi, Adeyemi, just do you have something to add, Kelvin?
Okay, you mean me?
Yeah, Kevin. Yeah, Kevin, right? Calvin.
Yes,
Adeyemi.
yes, sir.
Yes,
Hello,
Yes,
Adeyemi.
sir. Yes, sir.
I will try to add something because I have not been convinced why 3G or 4G will affect human beings differently. Maybe you can also do the research. The mask you used here, I don't know, maybe the mask, maybe it carries 4G radiation or 3G
Yes, it carries 4G.
Yeah, you can compare 3G and 4G and see the difference. To me, I think there's no big difference.
Sorry, sir.
Medical data to support the claim. I suggest you undergo the research and see.
Okay, sir. But the 2G and the 3G, so is there are some papers that I've read, the 2G has a less havoc to 3G, but we don't did our own on 4G, so that's why we do 4G.
The havoc in terms of radiation they generate?
Yes.
The effect on the organs in the human body?
Yes.
I think it's good someone has empirical data.
Okay.
Okay. So thank you for this interesting discussion on the effect of mass exposure for telecommunication on people. So I think we'll continue the discussion right now. Let me just check if there are two people who have not attended this section. Let me check if they are around. If no, we'll just continue the discussion during the small break that will come just after. So Eric Ziki is still not around. Emmanuel Faboro also. Okay. I think they are not here. So let me see whether they are not in the waiting room or sent a message. No. So maybe we can continue the discussion because now we are on break for, let's say, 5 to 10 minutes. Which one is okay for you, 5 or 10 minutes? Okay, let's say 10 minutes, and then we come back at past 15. So 10 to 4, and then we restart again with the last 3 presentation, and then we are done for today. So 10-minute break. Hello.
Yeah, 10-minute break is good.
It's fine? Is that fine?
All right.
Okay, because since I'm not hearing any feedback, it seems I'm speaking alone.
I think 10-minute break is good.
Okay. So see you at 10 to 4, and then we just at 10 to 4 time, Lome time. Okay. So,
okay.
Yeah.
Okay.
See you in 10 minutes anyway.
Okay.
Yeah. So we have to check if Dr. Segun Alaseni is around.
Yeah, he's there.
Okay, I saw him. And Mohammed Amza.
No.
Mohammed Amza is not here. And Mr. Peter Chibuke Okoye.
Neither.
Peter Chibuke Okoye.
Hello.
Yes.
Dr. Dembe. I'm sorry, Mr. Okoye is not, is strong, he's not well. Maybe he can present tomorrow.
Okay, let's see. If he's here tomorrow, maybe he can just send a message, and then we'll try to see whether there is a free slot.
Maybe he will be available if there is a vacant. Someone is not present, then can present.
Okay, that's fine. So, Mr. Simiu Maritabu, Nairobi, University of Nairobi, Kenya. Simiu Maritabu.
No,
okay,
she's not
here. Maybe she will connect after, let's hope. And so for now, we only have Dr. Segun Olaseni, please. So he can just start preparing for the presentation if he's around. Dr. Segun Olaseni, are you hearing us? Hello.
Let me call Olaseni on the ground.
Okay, that's fine. Thank you. Mr. Amza, who is Mr. Amza is not here as well. Okay, we just go. Okay. Mary, Tabu, Amza, we need to check if they are around or not. Is there any way we can contact them?
No.
Amza. Amza.
I'm here. Dr. I'm here.
Okay, you are welcome, Dr. Segun Olaseni, right? Okay,
yes.
Welcome
yes.
on board.
Okay.
Yeah, so are you ready to present?
Yes, I'm ready to present.
Okay, so we are presenting in 5 minutes. So
okay, just 5 minutes. Just 5 minutes. Okay.
In 5 minutes, we'll present.
Okay, in 5 minutes time, I will present.
The presentation will start in 5 minutes.
Time, okay, no problem.
Yeah. So just, you can start sharing your screen.
Okay.
And then we'll wait for 5.
Yeah.
And you start.
So now you are done with the medical physics.
Yes, now is the condensed matter section that is starting.
Hey guys, I feel like I should leave now.
Where is the coffee?
The coffee is online, Dr. Azote. Just request.
We can order the coffee on Amazon and then they will deliver it to your room. Can you give your address?
I am still in the office, so they can come there.
So they will deliver it to your office.
Yeah.
Your dinner will be directly delivered.
Okay, that will be nice.
So how is life in Italy right now?
It's fine. It's getting cold. Yeah.
Cold? People are not scared for corona?
Who cares?
People don't care. That is serious.
Not really.
Why is it not going?
But everyone put on his mask, so life continues, you know.
Oh, I see.
No stress.
The mask itself is a stress.
This corona story, I don't know when this story will end.
I'm trying to see how I will increase my slide.
You people are just overdoing it.
How to share it?
I think you shared before. It's maybe some.
Can you see my slide?
No, but I saw you before with the share icon somewhere. Can you do it again?
I should do it again?
Yeah.
Okay, let me do it again. Can you see?
Yeah, something is coming.
Okay.
Yes, I can't see right now, but
yeah, you can see now.
You can see now?
Yes. Okay, me, I can see.
Okay.
Okay, yes, we can see your screen. Please just put it on presentation mode and then we'll have it all done.
Okay. I want to board my slide.
Okay, go up.
As you go
up. Left.
Left.
Yes. Yes.
No.
Right. A bit right. The icon with the
the icon with what?
Square? Is it like a square and something? It's like a screen and something below.
This one?
No.
No.
Next to it.
Just next to it on left.
This one?
Yeah.
Yeah.
I should click this one.
Yes.
Yes.
Okay. I'll click on it. Okay.
It will come.
Yeah, it has come now.
Yes.
Good.
Oh, can I start the presentation?
Yes, I think so, because we are now okay.
Yeah,
So I think you can just start your presentation.
Okay, thank you for giving me the opportunity to present this paper in this webinar conference. Earlier on, the abstract I submitted for this conference is quite different from the abstract I'm going to present now. The reason being that the one I presented earlier, as at the time I sent that abstract, the work is not at the completion, more or less like the completion stage. But we ought to have had this conference long time ago, around August or so. In between, I was able to do some other work, and at the end of the day, I was able to finish the whole experimental work. Then I was able to write all my results. And that is what I'm presenting, because I'm publishing this paper with you. And that's the reason why I have to change my abstract and the whole thing altogether. I think I can continue now.
Oh, I think it's a good thing.
Yeah, I'll continue now.
It's very good.
So the title of my work is Conductometric Approach to Thermodynamics of Micellization of Anionic Surfactant in the Presence of Procaine hydrochloride. Procaine hydrochloride is an anisotrope. When we are talking about anisotropes, an anisotrope is more or less like something that can aggregate in solution, but not like surfactant. But most of the times, when they mix up with surfactant, they form a mixed mixer. But when they normally form a mixed mixer, they can easily form a mixed mixer when the concentration is high. But once we have it at a very low concentration, it only enhances the formation of micellization of any surfactant you mix it with at the end of the day. And that's one of the measures where I have to look at the thermodynamics of micellization of the anionic surfactant in the presence of this procaine hydrochloride. So introductions. Drugs are amphiphilic compounds, like I said. It's anisotropes. Anisotropes are all amphiphilic compounds. So drugs are amphiphilic compounds which consist of polar and non-polar. The polar are the hydrophilics, and the non-polar are the hydrophobic functional groups. So this group invariably dictate their therapeutic activities and ability to interact with surfactants. In furtherance, activeness of any drug can be moderated based on the kind of interaction they experience in solution. Since the incursion of the additives, this time around the additive is hydrotropes into an amplifier. The amplifier this time around is surfactant. We influence its physicochemical properties, characteristics, which are either degree of ionization, reactions rate, CMC. The CMC is critical micelle concentration, and thermodynamics parameter. We herein study the thermodynamics of micellization of sodium disulfate, which is an ionic surfactant, and sodium lauryl sarcosinate, which is also an anionic surfactant in the presence of local and anesthetic drugs, which is the procaine hydrochloride, because they are regular ingredients used in the industry. So methodology this time around, micellization of sodium disulfate and sodium disulfate in aqueous solution of procaine hydrochloride has been investigated using conductometric techniques in the, within interpretation range of 298.15 to 318.15 Kelvin within an intervals of 15 Kelvin intervals. The integrated form of Boltzmann-Sigmund equation were used to determine the critical micelle concentration and the degree of counter-ion dissociation. The CMC value, which is the critical micelle concentration values, show a minimum between 298.15 and 313.15 Kelvin. When the deep free energy of micellization were all negative, in the presence of procaine hydrochloride at all temperature studies. So adoption of a Lorry-Rangers compensation model shows that the obtained compensation temperature TC lie in the temperature range of 298.15 to 313.15, and that the massalization is entropy driven. So we have these materials there that we use for the work. We use the ionized water. Electrical conductivity values of the water is between 1 and 2. The pH of that water is between 6.8 to 7 at room temperature. And then the sodium disulfide use this Bauitra from Bauitra, which is about 99.0%. The sodium lauryl sarcosinate, we gave it a shorthand of SLS, is 98%. All are purchased from Sigma Aldrich in US. And then the propane hydrochloride also, we are purchased from AKSES USA. We have analytical grade, and we are subsequently used without further purifications. You can see the structure of those compounds used for this work here. This is the structure for the SDS, which is sodium disulfide. Sodium lauryl sarcosinate is here, and the propane hydrochloride. So the methodology is just what we have here. It's just a matter of just prepare a solutions of what we have, and then we put within a particular, like for example, stock solutions of 4.6 minus 4 or PHC in pure water were prepared and used as solvent for the preparation of surfactant solution. So the surfactant solution in the concentration range of 0.0041 to 0.1197 mole per DMP of SDS and 0.0073 to 0.021 21332 mole per DMP for SLS. All these concentration range are between pre and post micellar regions for the two surfactants. So electrical conductivity values were used, and just like that. And at the end of the day, what we do, by the time we mix it up, we equilibrate it, and at the end of the day, we measure the CMC of we measure the conductivity values of the solution in the present and in the absence of what do you call it, PHC, both for SDS and SLS solutions. And at the end of the day, you know, I told you two different methods were used for the measurement this time around, were used to characterize it. You know, the CMC values really is what is very germane here, because the CMC value will dictate values for all the thermodynamics parameters. From the CMC value, you get all the thermodynamics parameters. And of course, the first method we use for determination of a CMC is the one using the conductometric method. So we have to plot our conductometric method against a concentration of our solution, that is the concentration of the surfactant. So we have a linear graph, and all of a sudden you have an abstract chain. At that point where we have abstract chain, you trace it down to the x-axis, then you look at the concentration at which that change occurs. And that is where we call CMC, which is the critical micelle concentration. Then again, we use Boltzmann's Boltzmann method to determine the CMC as well. This time around, it's a matter of using a software. We call it software, we call it scientific agent. That is what I use to determine the CMC. But this time around, it looks so theoretical compared to the real experimental work. And that can be shown in the slide here. If you look at what I have here, I have SLS plus water here. The graph you can see here, this is the Boltzmann method, and the one you see here is the other one here is the one using conductometric method. So here, for example, if you look at this point, this is the CMC here. We trace it down, and this is the value here. But mathematical using that software here is going to dictate to us from that software. After we have slotted out our value, then we obtain what the CMC is equivalent to. That is SLA, that is sodium lauryl sarcosinate plus water, and sodium lauryl sarcosinate plus PAC, and SDS plus water, SDS plus PAC. So you can see we have the variation of specific conductivity and differential conductivity with SDS in water, B in 4.0 transfer for minus 5 mole per DMP PHC, and in water and 4.0 to minus 4 mole per DMP of aqueous of PAC at different temperature. So we have some values here after all what we want. After we must have determined all our CMC values, we have other value that needs to be obtained, which is the counter ion of binding, the beta value. The beta value is just the beta value is just what you need. The slope you obtain at the pre-micelle, you divide it by the slope you obtain at the post-micelle, region. That is what is going to give us this beta values here, and this is the CMC here. So that's to say that when we are dealing with SDS alone without PAC at different temperature, we have from this temperature to this is the CMC value. This is millimolar. It's a millimolar here. Value here is the millimolar, and this is the average values here for all what we have here. So for SDS, we plus PAC, this is what we have at different temperature for CMC, and this is also what we have for the beta value. So also for that of SLS values in water alone and with PHC. So we go ahead this time around to run all the thermodynamic parameters values with the enthalpy, the gift-free energy, the entropy value at when it is with water and when it is with so the columns, the first columns you have here is with water, that's SZ plus water. You see all the negative values for delta G, delta H, some are negative, some are positive, so that for delta X here, which is the entropy values, you can see what we have, and for SLS plus water also. So for SDS with PHC, these are all negative values for delta G, and the same thing delta H, the same thing delta X, all like that. Then I move on to, I've already explained my graph this time around. Then we try to look at chi-CMC values. The advantage of this chi-CMC value is to be able, okay, what is this? The advantage of the CMC value this time around, the chi-CMC value here were run using a model also. And that model really shows, that model were run, we use our data to run the value for chi-CMC at different temperatures. And we plotted it when we have SLS with water and when we have SLS with PHC. And also we did the same thing for SDS when we have it with water and when we have it with PHC. We try to look at the incursion of the PHC with SDS and SLS. And that is what this is the graphic way of looking at the way the two of them react. The first one here is the surfactant solution and plus what we call the PHC. And this is what we have at the end of the day. This look at a schematic diagram showing possible location of PHC in SDS and SLS in micelle solutions. So we also have, just for clarity's sake, so as to prove the entropy enthalpic compensation. So we needed to plot the delta H against T for SLS, SDS in water, in water, and as well in the with a PHC. This can see this will really determine the linearity of this determine the entropy compensation for the micellization. Once we have the linear form of this, then the model is confirmed. And in conclusion, from the connectivity studies, the following conclusions were made. PHC value has greater interaction with SDS than XLS, thereby leaving an impact on both CMC and thermodynamics function. Then again, with the degree-free energy, value obtained was negative, and the negative was more enhanced in SDS plus PHC and SLS plus PHC rather than in ordinary water, with increase in the temperature. So the negative correlation between there's something is missing in between here. The negative correlation between the degree-free energies and the temperature increases shows that the micellization process is thermodynamically feasible and adequately spontaneous. So, and it can be later concluded that the micellization process was both entropic and enthalpic driven, which changes from entropic to enthalpic as temperature increases. This is an indication for entropy composition phenomenon. Thank you.
Okay, thank you so much, Dr. Olaseni, for your nice presentation And I guess people have several questions for you.
Okay.
So this is the time for questions, and we still have 6 minutes for questions because you finished ahead of time.
Okay.
So you have the floor.
Okay, sir.
Just raise your hand if you have a question, and then we'll just let you ask your question. So I can start if no one is raising their hand. So I want to know from the first, the slide where you showed the curve for the CMC, where you find the CMC.
Yes.
I want to know, you said like one of them was the derivative, the first derivative, but
Yes,
I didn't fully
first
understand.
derivative.
Yeah, could you please show the slide?
Okay, I'm on with the slide, sir.
Yeah, no, not this slide. The
Okay, I
slide
should go
where you
to
have
that, this here.
Yes, this one.
This one. This is the one at the mid. This one here is the first derivatives. This is the first derivative method, and this other one is the experimental method.
Okay. So the first derivative method is a method, not a mathematical derivative of this curve, right?
Yeah, you know, I mentioned Boltzmann method, which I told you is just a way of inserting all my data into a particular model. And the model, we normally call it a scientific gender. So is we can call it a table curve. Or we call it a table curve. There are two of it, either scientific gender or table curve. Just slot in your values. By the time you run it, then it will give you CMC directly. Unlike the one you have to go, unlike when you, unlike what do I call it? Unlike the idea of measuring concentration, idea of measuring conductivity directly from the conductivity machine and plot it against concentration. And the linear, where you normally have a linear graph, at a point there'll be an absolute change in the linearity, then you trace down and obtain it. But in the case of the other one, which is the first derivatives, the first derivatives has its own method that is quite mathematical. And what you need to do, despite all the conductivity value obtained, all the conductivity value obtained again, so you are going to put into the model against concentration also. But it looks more, it gives you more accurate, gives more accurate answer, accurate result, more than the experimental one. But most of the time, we try to compare, because it's just like a comparison now of what we have for the first derivative one and the other one, which is pure experimental analysis.
Okay.
I'm on.
Hello, I think I went away for a while.
Okay.
Yeah, I'm just back now.
Okay.
It's an internet problem. So I'm sorry. I was asking if this is just a method or is a real derivative, because it's not looking like.
You asked whether it's a method. It's another method of determining C. It's another good method of determining CMC.
Okay. Okay.
Yes, another method of determining CMC.
Mathematical derivative.
Yes, a mathematical method of determining CMC. Yes.
Okay, I see. So do we have other questions inside? Are there any other questions? Okay, Dr. Yeah, Dr. Taureg Olabi.
Okay.
I need, I think, Doji.
Yeah.
Doji?
Actually.
Okay, could you promote?
Actually, I don't have a question, just to thank Dr. Laseni for his good presentation. Very good presentation.
Yeah.
just to thank him for the well done job he has presented. I don't
Okay,
really
thank you.
have a question because what he presented is clear to me, I think.
Thank you.
Yes. So I think it's a very nice job, and since
I
he
have a
also has
question.
okay,
Okay,
yes,
I'm waiting for a
Dr.
question.
It's not really a question, but I just wanted to understand better the current slide. What makes the difference between the one we have at the top and the one down? Like, yeah.
They are different. They are different. For example, the one at the top here is sodium lauryl sarcosinate plus water. This is sodium lauryl sarcosinate with PHC. And the one down is sodium dodisulfate with water. And the other one here is sodium dodisulfate from the PHC. So they are quite different from each other.
Okay.
Yes.
Yes, it's different compounds.
Yeah, they are different compounds, okay, but they are still all anionic surfactant reacting with anhydrotrophs.
Okay.
Yes.
And
yes.
what are you trying exactly to show?
What we are trying to look at, normally, let me put it this way. PHC, which is procaine hydrochloride, is a drug. And at a particular concentration, when you mix it up with surfactant, let me just put it this way. I think the best way to just ask this question is that, what is the advantage of GIGS in our normal life? Yes, that would be the best way. In our normal life, there are so many things we are using surfactant for. We use it for wetting, we use it in dye industry, we use it for recovery of oil, and for so many other things like that. But what dictates the usefulness of a surfactant at a point in time is the CMC value. If the CMC is very low, then you are very lucky. You are not going to spend much. So an hydrotroph, which is the PHC, I will add it to surfactant. If you can be able to force down the CMC of what you have, you are working well. And that is the advantage of what we are having here. So we try to look at, well, at what temperature can we have a good CMC? At what concentration? At a better concentration of the hydrotroph, which is the PHC, can we have a better surfactant use in any of our industry? That's the essence of this one.
All right. Thank you very much for the nice presentation.
Thank you, ma'am.
Yeah, and then there is a very good fit with the experimental data.
Yeah.
So yeah, I think it's a very good job. Yeah. Is there any other question? Okay, so if there is not, we just thank Dr. Olaseni for the presentation.
Thank you, sir.
Thank you, sir.
Thank you, sir. Along with other presenter.
Yes, we have to look for the next presenter. If they are not around, I think we will get close to the end now. So Mohammed Hamza and Mary Tabu. I don't know whether they are around. Mohammed Hamza and Mary Tabu. Mohammed Hamza from Itemba Lab, South Africa, and Mary Tabu from Nairobi, University of Nairobi in Kenya. Both of them are not here. Maybe tomorrow they will show up. If there is a free slot, then they will present. Then I think if there is no other question, is there any other question? We can close today's section. And then people will have more time for rest.
Okay.
Before tomorrow morning at 9.
At 9.